Hey everyone. Um, yeah, just testing the mic right now. Yeah, so yeah, it's 17 now, so let's get started. So I'm Shaker, and together with Ashish, who's also another in-person organizer for this workshop. So we'll be kind of going over the introductory remarks first, and then we'll get started with the talk, with our talks. So so we were very excited to present the RoboAdapt workshop, learning to adapt and improve in the real world. And just if you want to follow along on the papers and see like the schedule, we have this RoboAdapt Google Sites website that you can find. It's also on the CoRL website. So what will we be discussing here? So we have a bunch of speakers working on some very exciting ideas, and both the posters and the spotlight presentations covered this and a lot more. So some potential areas that are that are really interesting to us that we want to explore, specifically in the context of robotics, is continual learning, self-supervised exploration, sim to real adaptation, adaptive systems for human robot and multi-robot interactions, fine-tuning offline trained policies, and different applications in adaptive systems like to manipulation, navigation, legged locomotion, autonomous driving, and so on. So so we are the organizers. We have, so I think maybe the organizers can start in this order to introduce themselves. Maybe we'll go with the virtual organizers first. So Annie, could you quickly, yeah, let me, yeah. Can you unmute Ben? Can you unmute Annie and mute me? So I think you unmuted.
Hello, can you hear me? Cool. I'm Annie Shen. I'm a fourth year PhD student at Stanford University. I'm interested in robotic systems that can autonomously and continuously learn in increasingly complex environments. And so concretely, I'm interested in robotic reinforcement learning algorithms as a tool for this continual learning.
Hey, I'm Unnat Jain. I'm a researcher at Facebook AI Research and a visitor at Carnegie Mellon University. I love to develop visual systems that can learn from large-scale human interactions and can be deployed in natural settings in the real world.
Yeah. So I guess Ashish, I'll introduce myself first. So I'm Shikhar. I'm a fourth year PhD student at Carnegie Mellon University. So I'm really interested in building robotic systems that can work outside the lab, specifically leveraging passive knowledge from humans and the internet, like videos, etc. So yeah, that's why this workshop is very exciting for me. Ashish.
Hello everyone, I'm Ashish Kumar. I'm a PhD student at UC Berkeley. I work with Professor Jitendra Malik. I work on learning to adapt and improve in the real world, and some of my work focuses on rapid adaptation on legged robots, and I have some other stuff which tries to extend similar ideas to use vision and also continually learn as they exist in this real world.
Yeah. And then one of our organizers also working a lot on learning to adapt robots in the real world, especially legged locomotion, is Laura from Berkeley, who was not able to make it today. And then our senior organizers are Byron Boots and Jitendra Malik. And then so let me go through the, sorry, let me just mute this. So quick recap of the schedule. So we'll start at 9:30 with a talk. Actually, Davide Scaramuzza had a last minute emergency. So his PhD student Yunlong will be presenting. similar, basically very similar type of work. So that's pretty exciting. Then from 10 to 10:30, we'll have our first set of spotlight presentations where each presenter will have 7 minutes to talk and 3 minutes of question and answers. From 10:30 to 11 a.m., we'll have Haewon Park talk about her work. From 11 to 11:30, we'll have Deepak Pathak. From 11:30 to 12, we'll have another spotlight session. And then from 12 to 12:30, we'll have Angela Scholle give a virtual talk. From 12:30 to 2:30, we'll have a lunch break and the opening session. So it's relatively long break. And then after 2:30, we'll have our final talk of the day with Chelsea Finn. And then from 3 to 3:45, we'll have a panel discussion with some of our conference workshop speakers and some guest panelists from the spotlight papers who these are papers that we really wanted to highlight, and maybe the audience would have more questions about them. So we'll have a mix of speakers and authors as well from these papers. And then finally, we'll have a virtual and in-person poster session. So, thank you for those who came to the early morning virtual poster session. That was very cool. So this will happen on this 0th floor of the ONG building. And closer to time, I'll give, if any of the authors are present in the audience, I'll give more instructions on which paper goes where. We'll finalize this at lunch. And finally, last 15 minutes will be the closing remarks and the award ceremony. Yeah, and then, so again, our speakers, so we have, unfortunately, Davide Scaramuza could not come, but we have Yunlong, his PhD student from University of Zurich. We have Haewon Park from MIT, Deepak Pathak from CMU, Angela Scholle from University of Toronto, and then Chelsea Finn from Stanford. We also have Deepak and Chelsea come back for the panels, and then we'll have a few guest panelists, both in person and virtual. Dinesh Jayaraman from University of Pennsylvania, Victoria Dean from CMU, and then Laurel Pinto from NYU. So very excited. And we can potentially start to get set up for the next talk. Yeah, if there's any questions, you can also ask about the logistics or the schedule. Let's just see. Yeah, Yunlong is already in the room. So could you unmute him and allow him to share his screen, Ben? Yeah. Oh yeah, and just logistics. So if you have any questions for the talk, we'll have a 5-minute round at Q&A round at the end for the in-person audience, and for the Zoom audience, just put your questions in the feed loop chat or the Zoom chat. All right.
Okay, it's 2 minutes to 9:30, so I'll just go ahead and introduce Yunlong. I think his background is pretty much summarizing a lot about his talk. He's going to be talking a lot about agile drones, and I'm very excited to hear about it. Yunlong is a senior PhD student at Robotics and Perception Group with Davide Scaramuza at the University of Zurich and ETH Zurich. He's completed his master's before with Professor Jan Peters at TU Darmstadt. He's done a lot of exciting work at the intersection of reinforcement learning and optimal control with a focus on real-world applications, which makes it very exciting for this workshop. I'm very excited to hear more about his work with Davide on agile drones. Take it over, Yunlong.
Okay, so let me optimize for video clips. Okay. So yeah, good morning. So my name is Yunlong, and I'm currently a PhD student at the Robotics and Perception Group. And today I'm very excited to share my research on reinforcement learning and also its application for agile drone flight. So, okay, so drones are super agile robots that can navigate at very high speed through very complex environment. And in this video, what you're watching is a professional human pilot that is controlling a racing drone in very complex environment, at the same time competing against many other opponents. And for human, it takes many years of training in order to achieve this level of control performance. And one of the questions that our lab tried to answer is, what does it take to achieve the same level of control performance, or even better, with autonomous systems? And to answer this question, and today in this talk, I want to focus on two of the projects that I've done. The first one is about reaching the limit in autonomous drone racing using reinforcement learning. And in this work, we show that a neural network policy trained purely in simulation that can achieve, can push the drone to its maximum limit. And also it outperforms several optimal control-based methods. It also outperformed the best human pilot. And in the second project, we also kind of try to combine the advantage of both reinforcement learning and also modified control. We propose a new framework called Policy Search for Model Predictive Control for the application of flying through dynamic gates. So the task of autonomous drone racing. So in autonomous drone racing, the goal is to pass through a sequence of gates as fast as possible. And we can formulate this problem as minimum time optimization problem. And here, the optimization objective is to minimize the total time spent on passing through all these gates. At the same time, it has to subject some constraints, including the system dynamics, the input constraints, the state constraints, and also the physics constraints. And this is very difficult optimization problem. And if you want to solve with like using numeric optimization, it is very challenging because it's a non-convex problem. And instead, what we propose is try to use reinforcement learning to tackle this problem. And the main idea is to train a neural network policy that can map the state observation directly to the control command. And here the main question is, how can we learn this neural network? And we use model-free reinforcement learning because we can formulate this the reward very nicely. And the problem is that we need to optimize this policy such that this reward is maximized. And what is the objective in drone racing? As I said before, the objective was to minimize the time, but the time is very sparse signal. And only after you finish the lab, you can obtain a single variable indicating how good is this entire trajectory. And if you want to learn kind of the optimum policy for this single sparse reward problem, it is very challenging. Instead, what we propose is to maximize the gate progress. So on here, on the right-hand side, the vertical bar is representing the gate from top-down view. And the center of this vertical bar is the center of the gate. Therefore, our objective is to maximize the progress towards the center of the target gate. And the reward is formulated as, if there's no collision, then maximize the reward towards the center of this gate. If there is collision, then the agent receive a penalty of -10. And if there is no collision, and at the same time, it managed to finish the entire track, then it gets positive reward. And we train this policy by maximizing this reward signal, and we use model-free reinforcement learning. Specifically, we use proximal policy optimization method. And we train our policy entirely in simulation. So we use the flight math simulator, in which we pairize 100 drones in parallel. So we simulate 100 drones in parallel. Also, we randomly initialize the drone at different positions, not only at the beginning of, not only at the starting position, but also at different positions along the racetrack. Throughout the training, this initial state is updated depends on the experience of these racing drones. So, and this allow us to not only collect a large amount of data in a very short time, but also it allows us to collect a diverse of data that can use for efficient policy training. So here we achieve superhuman control performance within only around 5 or 6 minutes of training with a standard workstation. And after training in simulation, then we directly deploy this policy, this neural net policy in the real world. So to push the limit, we build a race zone, and this race zone has maximum threat to weight ratio of around 12, which is the most aggressive zone ever built. And our policy can still push this zone to its maximum limit and achieve a peak acceleration of around 12 G, and also a peak velocity of more than 100 kilometers per hour. And here's a video showing the flight in the real world. Yeah. So that was very aggressive and very fast. But how does it compare to the optimal control method? Because optimal control method can also achieve very good performance in quadruped control or in zone control. So to answer this question, we study this question by using two optimal control baselines. The first baseline is called trajectory tracking. And in this case, time optimum trajectory was computed offline. Why offline? Because the full quadrotor dynamic is nonlinear, and the minimum time optimization problem is very complex. So it takes several hours to compute one single time optimum trajectory. So we compute this time of optimum trajectory offline, and given this time optimum trajectory, then we track this trajectory using MPC. So this is trajectory tracking problem for the controller. And then the second baseline is not about tracking the trajectory. Instead, it only relies on planned 3D paths. So this is called contouring control. And the optimization objective of the contouring control is to maximize the progress along the predefined path, at the same time, minimize the deviation from this path. And because this 3D path can be planned very efficiently using a kind of point mass model. Therefore, we can use online planning. So to this end, given the same task, which is autonomous drone racing, we can have 3 different optimization objectives. And they are trajectory tracking, contouring control, and gate progress. However, because the gate progress is not continuous and it's not differentiable with respect to the state, and therefore, this objective can be only optimized with the RL, and the trajectory tracking and the contouring control can be optimized online using optimization methods. So we want to compare the performance of reinforcement against these 2 optimal control baselines. So we evaluate these 3 approaches on the same track, and this is a top-down view of the trajectory flew by each approaches. So we randomly initialize each approach at 50 different random positions, and we flew 50 different trajectories. On the most left-hand side, we see the trajectory flew by MPC. And because there's model mismatch between the model used for optimization and the model used during deployment, we see that the MPC cannot track this trajectory perfectly. And as a result, most of the trajectory failed on this track, like of flying through gate 4 and 5, and they do not pass through the gate. But for the contouring control, because the path can be planned online, and there's also no time constraint for the optimization objectives, therefore it can follow the defined path much better than the trajectory tracking, and it leads to more robust control performance. And on the most right-hand side is the reinforcement learning algorithm. It can always achieve 100% success rate. And this table summarizes the result in terms of both lap time and also success rate. So we have 3 different approaches: trajectory tracking, contouring control, and RL. In terms of lap time, given a time optimal trajectory, trajectory tracking can achieve lowest lap time, but it has very low success rate. Any small model mismatches can lead to crash because the zone is already at its limit. There's not enough control margin for the MPC to counteract some small disturbances, and eventually it leads to crash. However, RL can achieve very robust control performance, even though there's model mismatch. So here, the nominal model is the model used for training RL and also the model used for optimization. And both realistic model and real-world model are not accessible for all three approaches. And RL can achieve a highest success rate in the real world with lowest lab time. Then we try to understand the question, like why does RL outperform optimal control in autonomous drone racing? The first the first axis is like, is it because of the optimization method? Or is it because of the optimization objective? Because here we are using different optimization method, and we are also using different optimization objectives. So to answer the first question, is it because of the optimization method? We conduct experiments by using two different optimization methods to optimize the same objective. So we use MPC and RL for trajectory tracking. And here we show when tracking the same trajectory on the nominal model, both approaches achieve the lowest lap time, the optimum lap time. But in terms of tracking loss, MPC achieves lower tracking loss. And also when we transfer to a realistic model, both approaches failed. They didn't pass through the gate. But in terms of tracking loss, MPC achieves lower tracking loss. This indicates that RL does not outperform MPC when tracking a trajectory. So then we investigate, is it because of the optimization objective? To answer this question, we conduct experiments to use the same optimization method, meaning RL, to optimize different objectives. And these objectives are trajectory tracking and gate progress. So we use RL for both trajectory tracking and maximizing gate progress. And we see in terms of lap time, trajectory tracking achieves lower lap time because the planned trajectory is optimal. And RL is near optimum kind of optimizer. It achieves a lap time that is very close to the optimum lap time, but still not as optimum as the one solved using optimization. But in terms of success rate, the RL trajectory tracking failed 3 gates, but the RL gate progress achieves 100% success rate. It didn't have any failure. And here we see gate progress allows more robust control performance. So our finding is RL outperforms optimal control because it optimizes a broad range of objectives, including task level objectives, which is the gate progress. And this objective allows more robust control performance and also better generalization to the real world. And our conclusion is the optimization objectives leads to better task performance. Then, because our goal is to outperform the best human pilot, to answer the question, can our RL policy outperform human pilot? In June 2022, which is this year, we invited 3 world drone racing champions. And they are Alex Van Over, and he's the DRL world champion. Thomas Bitmata, he is 2 times multi-GP international world champion. Marvin Shepard, he is 3 times Swiss Drone League champion. And we race against these 3 human champions to find out whether or not our policy can achieve a better result than the best human pilot. And the answer is yes. In June 2022, our drone achieves better racing time than these 3 human pilots. It achieves 0 point faster than the best human pilot. And this video shows the racing performance of our autonomous drone in a flying arena. So here's the video. This is the human.
That is beautiful.
Martin.
One day, I dream I can achieve that. Damn.
So what he said was that was beautiful, and one day I dream I can achieve that. So you know how impressive it was. And beyond genre racing, because in genre racing the problem is still relatively easy in the sense it is a problem of passing through a sequence of waypoints. But in the real world, most of the environment are cluttered environment. It cannot simply defined as an empty environment of just passing through some waypoint. So we also use RL for the problem of agile flight in cluttered environment. And we use the same approach, but different reward, different training environment, and different observations. And then we achieve also very good performance for this kind of task. And also our approach achieves much better performance than state-of-the-art optimal control method. And this video shows one of the flight performance in the real world. So we have a construct a kind of a racing environment, but in this environment, there are some obstacles in the middle. So it has to race at the same time, avoiding obstacles in the real world. So this drone can fly quite fast in the real world, at the same time avoiding obstacles. And this drone has a lower thrust to weight ratio than the previous drone. That's why it looks a little bit slower. And given different collective thrust, the drone can also fly through all the gates. So that was about the first project using reinforcement learning for the task of autonomous drone racing in the real world. And in the second project, we try to combine the advantage of both RL and optimal control. Because RL, both of them has their own advantage and disadvantage. For example, for training the RL policy, normally it requires a lot of data. In the previous example, we use more than 50 million time steps for the training. And for MPC, there's no training required. It makes use of the dynamics equation, so it can generalize to the real world and also solve the problem, optimization problem online without training. The fundamental question here is how can we combine the advantages of both approaches? And the idea is to take MPC as parameterized controller. In our previous project, we realized that optimization objectives matters for the task performance. But in most MPC problem formulation, one of the main difficulty is to formalize the problem, and design the cost function is very difficult. And here we can consider the cost function as parameterized function, and there are some unknown parameters. And the goal of policy search is to find the optimum parameters for this cost function. And we can then solve given these parameters, then we can solve this optimization problem and find the optimal control command. And how do we do this? We can model those unknown parameters as a probabilistic distribution, like a Gaussian distribution. And given this distribution, we can then formulate the search of unknown parameters as policy search, probability policy search. So in here, this plot shows the main idea. The theta is those parameters, and we can model this theta as a pi, which is the policy, and sample these parameters represent as Z. Given sample Z, we solve several MPC problems, and we maximize the reward that give us, in the end, the optimum policy, high-level policy. And we can solve this optimization problem, or we can solve this probabilistic policy search problem using weighted maximum likelihood. And this approach has closed form solution. Not only can we learn Gaussian policy for state independent parameters, we can also optimize Gaussian linear policy for state dependent parameters. And in this case, the mean of this Gaussian linear policy is a linear function that inputs can take some state as input. And the parameters of this Gaussian linear policy are the weight of this linear function and also the variance of this distribution. And finally, we can also optimize neural network policy for high-dimensional state-dependent parameters. And we apply this framework for the task of agile drone flight. The task is to fly through a dynamic gate. So here, the colored bar represents the drone. And our task is to fly through a moving gate like a pendulum and reach a goal position. So here the problem is that we have to fly through the center of this moving gate. And also we need to know where to pass through the gate. However, the problem is that we don't know where to pass through the gate because we don't know when should we pass through the gate. It's like chicken and egg problem. Without knowing the passing time, you don't know where's the waypoint because it's moving. And without knowing where to pass through the gate, you don't know the passing time. And what we propose is model this time variable as unknown parameters. And we learn these unknown parameters using policy search. After we learn these time variables, we can solve these optimization problems. And these optimization problems outputs the optimal trajectory as well as the optimal control command that we can directly apply on the robots. On the right-hand side, we can see a learning curve of these time variables. So the reward, they converge very efficiently with only several training iterations. And on the bottom, we can see how the distribution of this time changes. So at iteration 0, we have no prior knowledge about this time. So we just model this time with random mean and random variance. And we randomly sample some time variables. After training for 2 iterations, we can already learn sort of some distribution about these time variables. And with more training at iteration equal to 10, we can already find the optimum time for passing through the gate, which is around 1.5 seconds. And given these learned time variables, we can then solve this optimization problem. We can also combine with neural network policy for online adaptation. So here what you are watching are 4 different test cases. So the drone are initialized randomly at different position, and also the pendulum gate is also randomly initialized from different position. And at each control time step, there's a neural network that predicts this time variable. And given this new time variable, then the MPC optimize for a trajectory which represents as red dot in those plots. So they all managed to fly through the center of the gate. And then we also deploy this system in the real world. And here we design a pendulum gate, and also we have a physical drone. And the task is to start from this initial position and fly through the center of this pendulum gate. And here's the video. And this is a second video that shows just different runs, and the drone starting from different position, and the pendulum gate also released from different position. So here you can see that the orientation of the drone is also aligned to the orientation of the pendulum gate. This is because in the cost optimization, in the cost formulation, we also try to optimize the orientation of the drone such that it aligns with the orientation of the pendulum. And all these approaches, all these applications was done using the Flightmare simulator, which is an open source quadrotor simulator that combines the advantage of both Unity for realistic environment simulation and also some C++ code for the modeling of a quadrotor. And one of the advantages of this simulator is that it allows the interface within some very popular open source reinforcement learning algorithms, and also control algorithm or path planning algorithm. It allows for training controller for the quadrotor by parallelizing the environment, and can achieve very fast training speed.
Yanlang, we're at 5
Okay.
minutes for the questions.
Yeah.
If you want to quickly wrap up. Thanks.
This is the end. So in conclusion, in this talk, what I have shown is that RL outperforms optimal control in autonomous drone racing. It allows for the first time to outperform the world champions. And also, our study indicates that RL does not outperform optimal control in terms of optimality, but in terms of optimization objectives. The optimization objective leads to better task performance. And finally, body search can be used for design MPC cost. And with this, thank you for your attention. And our lab is hiring PhD and postdoc. If you're interested, you want to work on drones, please apply. Thank you.
Thank you so much, Yanlang. I'm gonna relay some of the questions from the chat and some of mine, which I noted down. I think one of the interesting things which you highlighted was with just 5 to 6 minutes of training in simulation, you were able to deploy these fantastic policies in the real world. Could you focus a bit on what are challenges and what were some measures you took to get the sim to real transfer? I think that could be interesting for a lot of people here.
Yeah, so the main challenge for drone racing is that the drone is always at the maximum performance, meaning there's no control left for something else. If you want to just check the trajectory, then you still have enough control margin for counteract mistakes. And in drone racing, you really want to push the drone to its maximum performance. And also the drone we build is extremely agile, and the aerodynamic effects are difficult to model. The battery drops immediately as long as you launch the drone, and those things cannot be modeled. That's why here, reinforcement learning is extremely useful, because on the one hand, you can randomize part of the parameters. On the other hand, you don't necessarily need to track a time optimal trajectory, which by definition is not accurate. You can just maximize the progress toward the center of the gate. And it also allows you to more robust performance when passing through the gate, because the gate, they are not very big gates. They are actually quite small gates.
Got it. I think a closely related question that comes up is the scope of generalization here. A more basic clarification question would be that how are these tasks defined? Some of the demos that you showed, what is the definition of the task? Is the trajectory predefined and known to the drone or not? What aspects of perception become important, and how you can tie that to the sim to real question that I asked before? So here, the task is well defined, meaning the position or the entire track layout is given beforehand. And there's almost no generalization in our task. And also, because we use MLP, which doesn't have any memory. So here, the task is really overfitting to this track and push for the maximum performance. This is also same for the human pilot. We invite the human pilot 1 week before the race and ask them to overfit to the racetrack to push their maximum performance. If we want to generalize to different tracks, then some other neural network representations can be very useful. That clarifies. And I think one question which I have is, these are all super exciting results. And what do you think is left to conquer in this space then? One of the main challenges is vision-based racing, because here human relies on camera images. However, our drone relies on very accurate state estimation, the video you saw. And the second one is multi-agent drone racing. Human can avoid opponents. However, our racing drone cannot. If there's a kind of opponents in front of it, it will just crash into it. So multi-agent aspect of this problem is also very interesting. Thanks so much, Yanlang. I think I'll pass on the baton to Shikhar and Ashish in person, and they can set up for the spotlight talk. Thanks again. Did I stop sharing?
Any other questions? All right. So let's move on to the spotlight talks. So they will be 7-minute talks followed by 3 minutes of questions and answers. Thanks, Yun Long, for presenting. Can we thank the speaker? Okay. So the first talk is Sheng. Can you are you on the virtual?
Yes, I'm over Zoom here.
Are
Can
you
you
able
hear
to
me?
share your screen?
Yeah, let me share my
Okay.
screen now.
Can you start? Okay. So the first talk will be an auto tuning framework for controllers using auto differentiation. It will be presented by Sheng Cheng.
All right, so hello everyone. My name is Shane Chang. I am a postdoc working with Professor Narahovakimian at the University of Illinois, Urbana-Champaign. So today I'm going to talk about our work on DiffTune, an auto-tuning framework for controllers using auto differentiation. So robots' execution of complicated tasks builds upon low-level controllers that deliver precise and responsive motions. So controller design is important for the tasks, but controller tuning is equally important. So in this work, we present DiffTune, which is inspired by the training techniques in the machine learning community and apply auto differentiation to controller tuning. So DiffTune has the nice features that it preserves the stability of the controllers by design. It is also compatible with data from a real system, and it is efficient and can be done in parallel to the system's evolution. So let's take a look at the problem setting. So we consider a discrete time dynamics and a controller. So both the dynamics and the controller are differentiable, and we denote the control parameters as theta here, which actively participate in the control law. So our goal here is to find the parameter theta so that the performance can be improved by reducing the loss, which we denote by L. So how do we do this? So we unroll the system into a computational graph as shown in this figure. So the iteratively updated dynamics and control law are being unrolled into, or say flattened into this blue plane. So the parameter theta here as the blue block goes into the architecture, goes into this graph through the controllers, and then implicitly affect these states. And then towards the end, we count the control action, the states to the loss function to evaluate the performance. So, and then we can obtain the gradient of interest, which is the gradient of the loss L with respect to the parameter theta. And then we can use gradient descent to update the parameters iteratively. So now the question is, how do we obtain the gradient L with respect to theta? So for that, we're going to do this observation first, that the target gradient here can be decomposed into this following form using the chain rule. And then we realize that, okay, so if the loss function is determined, then you can plug in the state and control action into these two terms, so you can get to evaluate these two terms. So what about the rest? So for that, we will use something called sensitivity propagation to compute these highlighted terms. We call them sensitivity states. So the sensitivity propagation, which is highlighted here, is nothing but just taking the partial derivative of your dynamics and control law to your parameter theta, and then you can obtain this iteratively updated formula. And this basically concludes how we can obtain our target gradient using this decomposition and the sensitivity propagation. So the advantages of the sensitivity propagation are that it runs in parallel to your system's evolution, meaning it's simultaneously running to the system. And also it can conveniently incorporate the data from a real system, making possible of online and real-time auto-tune. So at this moment, one may ask, why don't you use backpropagation? Well, the short answer is that these two advantages are not achievable with backpropagation. The first one is clear because backpropagation requires a backward traverse of the graph. So you cannot possibly expect it to run in parallel to your system's evolution. But how about the second one? How about incorporating real data? So let's take a look at why backpropagation is incompatible with real data. So first of all, let's recall how backpropagation works. So it builds upon this computational graph, and the way it works is that they will traverse forward first from the theta parameter to the dynamics and control and the states, and then going to your loss function. This is the forward path. And then for the backward path, we'll go backward from the loss to the theta to compute the gradient information. So a key observation here is that when you traverse the computational graph, when you want to obtain a new state, for example, if I want to obtain this xk, then I have to supply to my dynamics of my previous state xk minus 1 and my control action uk minus 1. But so you see that for us to obtain this new state, we have to evaluate the dynamics. But this is really not the case with a real system. So a real system is an integrator itself. It's a physical process. So the way you can obtain or infer about the state of a real system is either through sensor measurements or state estimation. So in other words, when you have a real system, you can never traverse the computational graph because this part is broken. And then the broken graph forbids the usage of backpropagation to compute the target gradient for a real system. Okay, so now let's see how DiffTune works on a system. So in this case, we have a quadrature as the system, and then we have a geometric controller, which contains 12 parameters to be tuned. And we apply DiffTune here, and as you can see that this blue actual trajectory gets closer and closer to the red trajectory that stands for the desired trajectory. And you can see that the loss here, which is the root mean squared error, is dropping through the iterations, indicating the effectiveness of using DiffTune for changing the parameters. And towards the end, we get 5 times reduction. And coming up next, what I want to say is, in reality, there are uncertainties that are not reflected in the nominal model. I think Yunlong just highlighted this part in his MPC work. So in this case, the uncertainties can contaminate the gradients if you are going to compute them based on your nominal dynamics. And that will lead to inefficient parameter update. So here, our solution is to apply the L1 adaptive control to compensate for the uncertainties during the tuning procedure. So intuitively, the L1 adaptive control forces the uncertain system to behave like the nominal uncertainty-free system, which preserves the validity of the computed gradients. So on the right, we show an ablation study that illustrates the individual rows by DiffTune and by L1. So you can see that each individual can reduce the tracking error. But when you compare these two cases on the right, you'll see that with DiffTune and with L1, it really helps to preserve the validity of your gradients. And towards the end, we use the same number of iterations for these two cases. And with L1, you can reduce the tracking error to further down than the case without L1. So I think I'm a little bit over time, and my computer seems to be frozen. So let me restart my slides real quick and then jump to the conclusions. Sorry about that. So I'm going to highlight this generalizability really quick. So one thing we have for controller tuning is that, let me go to the previous slide. So there are, different working conditions, or called operating conditions for systems, and we don't necessarily tune the control parameters for one trajectory or one system. Instead, we tune for the operating region of that. So we adopt the the training and test side technology from the machine learning community, and then do the training with this, training, validation, testing side. And the results are that we can generalize the tuned parameters to even the cases that are never seen before in this training set. So to summarize, we propose DiffTune, which is an auto-tuning framework using auto differentiation. And then for ongoing work, in one direction, we're working on the open source of the DiffTune as a toolbox, meaning that you can supply your dynamics and controller, and then you can use DiffTune to improve the performance. And on another direction, we're improving the tuning efficiency by investigating the hyperparameter-free approaches, where we also show deeper insights behind the DiffTune. And we call it DiffTune Plus, and the preprint is available on arXiv. And lastly, we're working on validate the DiffTune on a real platform to show its effectiveness, like a quad author. So that's all. Thank you, and I'm happy to take questions now.
Any questions?
Oh shoot, I didn't share my screen towards the end. Sorry.
So I have one question.
Sure.
So in this case, you show your results on drones. So drones don't have contacts. And in the framework that you mentioned, you said that we could supply our own dynamics and the objective function, and it automatically aligns the trajectories. How well does it scale for systems with contacts? Because I would assume that the dynamics are the hard part when it comes to complex forms of contacts, like either fine-grained contacts or things with slip or something.
Yeah, that's a good question. That's something we're trying to look into. Basically, everything I've been talking about today works for the system and the controller that are differentiable, which sort of exclude the cases that you're just describing, meaning that there are contacts which can cause, hybrid dynamics. So for that, I think maybe we can apply some subgradients just to use as a surrogate for the gradients for the differentiable cases. And still, I mean, once you find the appropriate subgradient, you can still apply this technique to, gradually and iteratively improve the performance.
Got it. Thank you. Let's thank the speaker once more.
Thank you.
So the next talk is train offline, test online, a real robot learning benchmark. And so this is a pre-recorded talk because the authors couldn't make it. Annie, are you on the virtual link? Could you start?
Yes.
All right.
Hi, I am Gaoyue Zhou, a master's student at CMU. Today, I will introduce our benchmark providing shared hardware for evaluation, which we call Train Offline, Test Online, or TOTO. This is a collaborative effort between CMU, UC Berkeley, University of Washington, NYU, and Stanford University. In the TOTO framework, we provide a real-world dataset collected on our hardware. Remote users train offline policies of their choosing on this data. They submit these policies for evaluation on our real-world setup. The evaluation results guide future iterations of method development. These evaluations form a leaderboard, given direct comparisons on shared tasks, data, and hardware. Here's our robot setup. We have one 7 degree of freedom Franken Panda robot arm and one RGBD RealSense camera providing image observations. We use a common joint position control stack that runs at 30 Hz, where actions are specified as target joint angles. Our dataset consists of the following components at each time step: the proprioception state specified as the current joint angles, actions specified as target joint angles, RGBD image observations, and the reward. Our training dataset contains two tasks: scoping and pouring. We show some representative trajectories with varied objects, materials, lighting, and target locations. We can see that both tasks requires changes in orientation of the gripper, which makes end-effector control using only target locations insufficient for solving our tasks. We measure the weight of the material successfully scooped or poured as a reward. Thus, both tasks have sparse reward. The initial release contains 2,000 scooping trajectories and 1,000 pouring trajectories. We use 3 ways to collect our dataset: teleoperation, BC rollout, and trajectory replay with noise. During teleoperation, the human controls the robot in an intuitive and effector space using an HTC Vive virtual reality headset and controller. Most teleoperation trajectories are successful. After teleoperation trajectories are collected, we train simple state-based behavior cloning policies on each target locations, so no visual perception is required. Finally, we also replay individual teleoperated trajectories with added noise. Here we show the statistics of our dataset. Pouring data collection using replay and behavior cloning proved to be challenging to reset, so it was nearly all collected with teleoperation. The first question we address with Toto is, what makes a good visual representation for robot learning? To answer this, we train behavior cloning policies on top of frozen pre-trained representations. We evaluate these policies on our shared hardware, and the results inform us about which representation works better. We evaluate 5 such visual representations, each contributed by remote users. We have 2 representations that are trained on our dataset, BYOL and MoCo, and we call these in-domain. These are in contrast with more generic representations, MoCo trained on ImageNet, ResNet50 trained on ImageNet, and R3M trained on Eagle4D. Here we show evaluation results of BC with each representation. The best performing ones are the 2 in-domain models. Pouring requires more location precision than scooping. All methods see a small performance drop moving from trained object locations to unseen test locations. We show the quantitative result of our visual representation experiments. In general, the relative performance between models is mostly consistent across scooping and pouring, with MoCo in-domain the best performing one. We also observed that the performance on testing locations does not degrade significantly compared to training locations, showing that the representations have some generalizable notions of where the object is. We also asked Toto, what's a good method for offline policy learning? Remote users contribute 4 initial methods: behavior cloning on the successful trajectories, Fin, which select actions using nearest neighbors, IQL, which is an offline RL method leveraging expectile regression to avoid any out-of-distribution queries, and decision transformers, which recasts offline RL as sequence modeling. Fin uses the BYOL model, and the other 3 models uses the in-domain MoCo model. Here, we evaluate policy learning method on scooping. Fin and BC perform the best, both of which uses in-domain vision representations as well as quasi-open loop rollouts that predict and execute 50 times step trajectory without replanning. Fin sees the biggest drop between train and test locations, which makes sense since they select actions from the training dataset via k-nearest neighbors. DT is unable to solve the pouring task in train or test locations. Fin achieves no success on test locations. BC and IQL both see successes on test locations, but still experience a significant performance drop. Here are the quantitative results of our policy learning experiments. We observed that Fin performed the best on train locations for both tasks, although it fails to obtain successes on pouring test locations due to the precision requirement of the task. Meanwhile, all other methods also experience some level of degradation when moving to unseen locations, leaving one clear direction for method improvement using Toto. We're soliciting additional baselines. Submit your favorite vision representation or policy learning method today. To encourage participation from different research communities, we support multiple forms of submission. As we've seen before, Toto has this pipeline where we input both the encoded image and the proprioceptive state into the policy, and it returns an action which is then executed on the real robot. In the scenario where a user wants to contribute a vision representation model, but they do not want to develop a policy, they can still contribute to Toto by focusing on the highlighted image encoder part of our pipeline. They will simply train their model, provide two interfacing functions to load their model and any image transforms if needed, and then use our provided scripts to generate embeddings and train BC agents. Finally, they will submit their vision representation model and the BC agents, and we are ready for evaluation. In another scenario where the user would like to contribute a state-based policy, they can instead focus on the highlighted part of the pipeline. We have released all the total visual representation models, and they can be easily used with our interface. After training your policy, similarly, you will implement two functions interfacing with our stack. And then we're ready for submission. Lastly, we also support innovating on the entire agent. You will simply train your agent, which may have any custom structure. You will then implement two interface functions, and we will be ready for submission and evaluation. For more details, please see our website, which includes details on our open source dataset and starter code. We believe Toto picks a path forward for robot learning by lowering the entry barrier. When designing a new method, a researcher can train their policy on our dataset, evaluate it on our hardware, and directly compare it to the existing baselines for our benchmark. As we support submissions for either only the vision representation model, only the policy, or both, we effectively foster collaboration between the computer vision, robotics, and algorithmic design community on the task of building more intelligent embodied agents. Meanwhile, our result on the initial set of benchmarks shows that our task suite is challenging yet possible, providing room for growth as users iterate on Toto. Thank you.
So we can hold off the questions to the panel discussion in which some of the authors of this paper will be there. Let's move to our next presentation. So the next one is watch and match supercharging imitation with regularized optimal transport, and it will be presented by Siddhant. Yes, go ahead.
So, hi, I'm Siddhant, and I'll be presenting a work titled Watch and Match Supercharging Imitation with Regularized Optimal Transport. This is joint work done with Vaibhav Mathur, Dennis Yaratz, and Laurel Pinto at New York University. So in recent years, we've seen some robots do really complex tasks, such as solving a Rubik's Cube, doing parkour. And when I started my PhD a year ago, watching these videos made it feel like robotics is solved or like close to being solved. But a closer look into these systems reveals that they need a lot of time and effort in order to make them work on these very narrow scenarios. Imagine you want to teach a robot to do one of these tasks. I'm sure none of us would want to spend hundreds of hours to teach these skills to a robot, only for it to go to waste when the scenario changes. So in this work, our goal is to minimize the time and effort required to teach these skills to a robot. So how should we teach our robots? A common way of teaching something to someone is through imitation, which is the principle of watch and match. Watch what someone else is doing and match their actions. A popular method for imitation learning is behavior cloning, where an expert makes a robot interact in the environment to collect some demonstrations, and a policy is trained on these demonstrations using supervised learning. Now, though these methods seem to work well, they tend to require large amounts of data, which in turn needs a long time to collect. Now, since we want to minimize the amount of time required to teach these skills, let's look at what happens when you do behavior cloning on a small data set. Consider the task of opening a box. In this case, we provide a single expert demonstration using a joystick, and train a behavior cloning policy on this demonstration. We observe that the BC policy successfully completes the task when starting from the same initial position. But if the initialization is varied even by a little bit from that in the demonstration, it struggles to complete the task. And this is a common problem with behavior cloning, referred to as the distributional mismatch problem. So a fix for this is to just continue fine-tuning the behavior policy using online learning. So given an expert and an agent trajectory, we use an encoder to obtain a trajectory of encodings. This use of an encoder is necessary because directly learning a policy on these high dimensional visual spaces is difficult. So we just reduce it to a lower dimensional representation. Now, given these two trajectories, we obtain a measure of similarity between them using an optimal transport-based matching scheme. And we use this matching score as a reward to do inverse RL in order to fine-tune the policy. Now, even though this pre-training plus fine-tuning scheme seems reasonable, naively combining offline pre-training with online fine-tuning does not work very well. And this has been studied in previous literature. You can refer to these papers to understand why this is the case. So to solve this, we propose our algorithm, regularized optimal transport, where we do online fine-tuning with BC regularization. Our objective function consists of an RL loss, which is a Q-learning based loss commonly used in off-policy reinforcement learning. We add a BC regularization term to this, which is supposed to keep the policy close to the expert data distribution. However, always applying this regularization while training can bias the policy towards your expert data, which might be undesirable. So we add an adaptive weight, which is supposed to regulate the amount of regularization being applied during the online learning process, at different stages of the online learning process. So this is our simplified loss function. And the idea is to keep the policy close when pi BC is performing better than the current online policy. And in order to compute this adaptive weight lambda, we use the current equation. And lambda basically represents a proportion of states where the BC policy performs better. And again, the idea is to increase the amount of regularization applied when your behavior policy performs better than the ROT policy. So let's go back to the task of opening a box. Like behavior cloning, ROT succeeds when starting from the same initial position. However, now ROT also succeeds when starting from any initialization in front of the box. So like putting it all together, we start with collecting data. We provide a single expert demonstration. We initialize a behavior policy using behavior cloning, and we fine-tune this behavior cloning BC policy online with ROT. We allow this fine-tuning for only a single hour and obtain the final policy after an hour, which is able to generalize to these unseen initializations. We evaluate our approach on a set of three environment suites: DM control, OpenAI robotics, and the MetaWorld benchmark. These are our results, and we observe 7.8 times faster imitation on average as compared to prior work. We also evaluate our approach on a set of 14 real-world tasks. For each of these tasks, these high-dimensional RGB images are given as an input, and the policy is supposed to spurt out the end effector positions. For each task, we give only a single expert demonstration and allow a single hour of online fine-tuning. So yeah, these are our results. And as you can see, ROT significantly outperforms behavior cloning and other adversarial inverse RL-based approaches. Our work does have some limitations. One, we do need expert demonstrations in this case. So since the demonstrations are the only signal provided to the policy about the task to be performed, suboptimal demonstrations lead to suboptimal actions. And the second is that the model struggles in cases where the task features aren't visually distinct. We can understand this through an example. So this is an expert demonstration of the task of placing a peg inside the cup. And this is a failure mode in the learned policy where the peg, like the robot arm, places the peg behind the cup. And as you can see from these two frames, they're visually very similar, and it's difficult for the model to tell them apart. However, it must be noted that on the representation learning side, we do not use any pre-training schemes, and using them might help alleviate these problems. So this is our work, regularized optimal transport. Some key takeaways are that we learn from high-dimensional images. We learn with a single hour of online fine-tuning from a single demonstration. And our video and open source code are available at this link. Apart from what's been shown, ROT also successfully works on state-based observations as well as task-specific environment rewards. For more details, come meet us at our poster. Thank you. Yeah, so that's achieved through the optimal transport. Oh yeah, so the question is like is that the whole question? Or? Okay. Yeah. So the question is, how do you get the reward for the fine-tuning process? And what we do is, given an expert and agent trajectory, you can encode, so every frame in the trajectory can be encoded into a representation. And then we use trajectory matching using optimal transport, which is like a method for matching two distributions, basically. But the idea is you can do trajectory matching to get a sense of how similar the two trajectories are. And based on, the reward is basically how close you are to an expert demonstration, which is the closer you are, the better reward you get. And you just use that as a reward to train this without needing environment rewards.
In this, you use one demonstration and compute the trajectory distance to optimize in the real world.
Yeah.
Can this method leverage having, like, one of the properties you want in something which learns in the real world is that if I give it more demonstrations, it should learn faster than it would from just a single demonstration.
Yeah. So the simulation experiments are, so the DM control and the OpenAI robotics ones. So the DM control one is like 10 demonstrations and the OpenAI is 50. So for the real world experiments, we just realized that one demo is enough. So you don't really need more, but this is not limited to a single demonstration.
And do you see that how does it data? Like, you see that having
I remember, yeah, like I tested it out on the DM control and the OpenAI ones, because even in Meta World, only one is enough. But for them, having more demonstrations made it quicker. So. Cool. Okay. Thank you.
Unnat, are you unmuted?
Yep, I can go.
Yeah. Go ahead.
Okay, we are very excited to have a second invited speaker here. I'm happy to introduce Haiwan Park, who is a research scientist at MIT Media Lab. Her research focuses on socio-emotive AI. She works on personalization of socially embodied agents that support long-term interaction and relationship building with users. Her work is applied to a range of real-world domains, including early childhood education and healthier aging in place. Personally, I have found her robots to be just very adorable, and I'm very excited to know about the question she raises here today. Do artificial agents need social embodied intelligence? Take it over. Hi.
Thank you, Annette. I had to reshare my screen, making sure the sound is on. Yes, great to be here and just changing some of the topics to social robots from, I just got a glimpse of the spotlight talk that was about grasping. But yes, I'm going to refresh the audience to think about some of the social aspects that our robots bring too, right? And any robots that interact closely with humans needs social and social intelligence, right? In addition to being a principal investigator and research scientist at MIT, this year I'm taking my sabbatical and I'm working with the Amazon Lab 126. So I'm adding another line of adorable robots in my line of adopted robots. So I'm pretty excited with coming from academia, but applying my research and intuition to a commercial robot. So I'm pretty excited about that experience and happy to talk about it if you have questions. So like Una just gave a brief introduction, this past like 7 years at MIT, I really focused on adventuring into sending robots in people's real world, deploying them in people's homes, schools, like centers. And this is an ongoing effort, and it's like an unparalleled effort in number of robots and number of people we studied in the wild. I underlined human experience here because that's going to be the highlight of this talk in relation to how we measure human experience with behavioral cues. So yes, just to give some of the summary of the works that we've done in the past years, especially during the pandemic, we've increased the number of studies to support transitioning from school to home, supporting young children's education, right? It was a very timely pivot that we made to support parents who had to now double as kids' teachers, right? They had always had to be in their side, even when they were remotely connecting to their classrooms, because these kids are just so young, right? But we see a big impact, big societal impact in bridging the gap, reducing the gap in early childhood education, especially in a country like US, where students who, when they join kindergarten, mostly is the first public school system in most of the states. But when they first join kindergarten, they are a unique sample of their cultural background, their immigrant status. So it's like a very diverse set of students that enter kindergarten, and they just find out that, for example, their language and literature skill aren't like their peers who use English as their native language, right? So we see a big societal impact we can make in this domain using more personalized social agents like the robots. We've since then, since the pandemic, we've transitioned a lot of the study into the home, supporting, for example, training parents to how to interact with their child, how to have more rich dialogic interaction with them around the story time. Yeah, so really exciting adventure. Another line of research that we're doing is supporting older adults and their emotional wellness. So we've also been using the robot to be their like healthier, positive psychology coach. And we learned so much from these real world studies, how we should design, how we should position the agent, the robot, and how can the robot dynamically learn through the interaction with users. So big question here, how do we measure the AI success in the real world, right? In the lab setting, we run our F1 scores, like various metrics to evaluate our algorithms. But in the real world, when you deploy them, how do you measure the success, right? We need to then, the human experience is everything. Whether you're building a collaborative robot that helps assemble things in a, like a workplace or in a factory setting, or it's a social robot like the robots that I'm working on, supporting like their behavior change, like better education, their social emotional learning. At the end of the day, it's all about how successfully the robot delivered that goal and how users perceive their experience. Like, do they perceive it as helpful? Do they perceive it as supporting them, right? So you can think of like it as the human experience as a very subjective measure. It is. Some of the objective measures you can do is some people try doing like, you know, fMRI and actually measured if, like, for example, in many of the HRI studies, the baseline is the human-human interactions, right? So that's like the gold standard that you are comparing against. And some people use fMRI to see what areas in the brain light up, and they found out, you know, when people are interacting with social robots, similar areas light up as when they are interacting with another person. But we can't always look at brain images to evaluate their experience, right? The reason experience is also so important to measure, and sorry about my light, I'm in Florida, so we have very strong sunlight. Can't do much about it right now. So yeah, the reason like that convinced me that experience is so important, and like the relational aspect of the human robot relationship is important, is because every time we run a study, like we see that people who, you know, obviously have built a close relationship with a robot is showing better outcomes, whether it's education or healthcare, right? This is not a surprising finding if we look at like human-to-human psychology literature, but it is very interesting that people also treat social robots as another social actor, like another social being, right? So yeah, we just see this over and over again that, you know, when we ask people to rate how close they feel the robot is to them, you know, like for children, we develop age-appropriate measures to measure that. We constantly see this high significant correlation to their closeness to the robot and their outcome, in this case, the learning outcome, right? And we found out that this is especially true when the robot's behavior policy was personalized to them. In the healthcare domain, same thing, right? People who built more stronger working alliance with a robot were more likely to change their behavior and believe that they can change their behavior. And also, especially when the robot's behavior was supportive and companion-like versus more coach and more like goal-driven like. So just more of these findings are supporting us to really study the human experience, right? How can we help people build healthy relationship with the social agents that can improve their experience at the same time, achieve their goals, right? So how do we measure experience in real time? Not through brain imaging. How do we measure experience in real time through the behaviors that the robot can observe, right? So today I want to focus the talk on how to use human affect expressions as a cue, as an input, as a reward to developing the robust behavior policies. So let's get on to it. So today I'm going to focus more on the line of work that we did in terms of supporting early childhood education. The reason it being the social impact it's making, but also children are very interesting. So there are many models developed for adults, right? But adults we have like fully, wait, I'm just taking that back. Some of us haven't, but we have like have a mature development of our social cues. Like for example, adults are really good at faking engagement. And engagement is a really important cue in the interaction, right? But we are trained so much that we can fake engagement, but children don't. And their engagement cues are actually very unique. And that's where the personalization benefit can make even higher impact. So yes, it's an interesting problem at the same time, has really good social impact. So there you go. The aspects of the robust behavior that we are personalizing. So most of like the intelligent Turing systems, they personalize the educational curriculum, the content, right? But we are working on social robots. We're working on robots, right? So we are more about personalizing the robust behavior, right? So how can we personalize the robust role, for example? How can we make sure the robot's displaying the right affect at the right time, right? How can we improve the robot to take better turn takes, better dialogic turn takes? So let's talk about those aspects of personalization.
Hey, Teika, wake up.
Hi, my name is Tega. Nice to meet you. What is your name?
Ariana.
Ariana. Cool. I'm
Okay, I'll just stop it there for now. So what we are doing here is the robot is this is the first session of the many sessions that followed. So this is like the first session where the robot was getting to know the child was getting to know the robot, Pega, and they were sharing like a storybook. And the robot will tell a story to the child and the child will tell a story to the robot. And in that process, what we are analyzing is how much the child is engaged and how much the child is also learning. So we are measuring this through many different cues, right? So another personalization line of dimensions of personalization we are doing is in this
Lavender. I'm lavender. Oh,
What are we trying to find?
we are trying to find lavender color stuff.
Okay.
That's
The
not
word was lavender.
Yes. What is lavender though? What's lavender? No, that's blue. What is lavender?
So obviously the child is confused
Girl.
what it is
Jumping.
and chooses a wrong answer.
I'm sure you will do better next time. I believe in you.
Robot's turn.
Time to perform. Lavender is purple.
Yes. Just like my friend loves lavender.
So in this case, the robot is jumping in and taking a role of like a more knowledgeable peer, because obviously the child was having problem understanding the word lavender, right? So as the interaction goes on, when the child is now demonstrating more knowledge, the robot steps back and asks for help from the child. Hey, like I didn't really understand that the meaning of that word. Can you help me out, right? So by doing this adaptive role switching, well, we were able to see the child's engagement was really high. Like we maintained it quite high level. And also it was more effective at children retaining new vocabulary, right? So these interactions were all built using reinforcement learning. So basically, like simply put, the robot is constantly observing the child's state, like how much the child is engaged. Is she learning new knowledge or not? Is the level of the game too hard? Is the level of the storybook right for the child? And chooses an action. So whether the action be a role selection or changing the sentence structure to be easier or more harder. And then getting a reward based on the children's renewed engagement and renewed level of learning, right? So it's a balance between how much the child learns and also to not lose engagement, like how balancing between the engagement. So yeah, like we show how well our policies worked, looking at, like the benefit of the personalization algorithm, the policy. So on the very left hand corner, the upper triangle is showing like distance between, like the average distance between every policy that was trained per child and how different they were between two pairs of participants. And on the lower triangle is showing because like in the end, what matters is which is like the maximum reward action in a state action pair, right? So the lower triangle is showing what action the robot is selecting and how that is different per child. So you can actually see that the policies actually did quite personalized were actually trained quite differently for different participants. I think the more, in terms of measuring the task performance, so we see evidence of the policy being personalized, but what's the performance, right? So in the interaction in the real world, how we measure the success is basically how successful the policy was in achieving the goal of the task. And in this case was children learning new things and being engaged, right? So the signals consistently show that children were learning better and faster and actually retaining more knowledge when we went back after 2 months and retested children's knowledge. Engagement too, right? So we measured engagement through facial expressions, their body posture, and we found out great correlation between like how expressive they were in their facial expression and how engaged they were in their facial expression, as well as like their body posture, like how much close proxemics were they to the robot, and how much posture change they occurred. We also measured through physiological sensor, so children are wearing these wristbands. We did see some results, but the results of that was quite noisy. But we did see significant difference between personalized and non-personalized groups still. So the question, back to question is, like I was talking quite a bit about engagement, right? But then at the beginning, I told you that children are really interesting because they haven't fully developed faking the right social cues. So their engagement, actually, we noticed that from multiples of our studies, we observed that children's engagement cues were there was like a big spectrum across kids. That could be different culture they come from. That could be because they're in a different developmental stage, because not all the same age kids are in the same developmental stage. But for many of these reasons, like children's cues are very different, not just engagement, but they are, for example, back channeling behavior. And also like these like social cues have a big spectrum across kids. So we felt the need to train a personalized engagement policy. And even though we are doing this in a long-term scale, we also needed to develop something that can learn to personalize using very few samples, right? So the idea was this. The problem statement is that given videos of like, given the video frames of children interacting with robots, can we make a personalized estimation of the engagement level using as few possible labeled clips from the target child? So we will train a general policy, the group level policy, right? But then now when we see a new child, so we're creating a group level policy using existing data sets, but now when we encounter a new child, can we actually request as few number of labels possible to develop a personalized engagement model for this very child? So just quickly going through because my time is coming up, as I said. So the input is the video stream of the child robot interaction, right? It's segmented into fixed size intervals. And then they are passed through a pre-trained CNN, and then as input to the, so this is the proposed temporally consistent deep Q learning, as we called it. So the video frames are now getting inputted to generating labels and classification labels. So this is modeled using the LSTM cells unrolled over the time steps and followed by the fully connected linear layers. The outputs of these fully connected linear layers are then averaged over time and passed through a softmax layer, which outputs the optimal action for the target video, it being whether it needs to request for a new label or outputs the engagement level of the child if it doesn't need to request for a new label. So in the offline setting, the frames that needs label can be stored in the data layer and then can ask for human expert labels in a batch sense. In the online setting, when the robot is actually interacting with the user, we have like developed interaction mechanism for the robot to gain this label. So this can be often elicited as question asking. So are you still engaged? Or are you having fun? Would you like to do something else? So those kind of questions and the response from the user is then used as the new labels to train this personalized policy. Interesting? One good idea? Yes. So after each session of the child robot interaction, the engagement classification and labeling policy is personalized to the target child using the previously and newly acquired labels. And this is updating the parameters of the Q function. So jumping to the conclusion, yes, our model like outperformed. We basically used the group level policy in session 1. So session 1 through session 8, we evaluated. So in session 1, the initialized model, the group level policies used. And then we compared our TCD-QL, which is our model, against the LSTM-S approach and computed for accuracy and F1 score. I won't go into too much detail here because I want to go towards one last message before I wrap up. Just looking at more detailed results. This is like the delta accuracy percentage. It really works well in most cases, but we looked at cases where it didn't work well.
Toad ate and ate, but he was still hungry. Then he saw.
So obviously you can see in these two video clips that children are they are obviously disengaged, but their disengagement status is not captured because they are kind of like out of the field of the vision of the robot, right? So we see many cases that we need to expand on the sensing capability, but overall the personalized engagement detection worked really well. One last thing I also wanted to just note for people who are looking to use affect signals as engagement signals for human robot interaction or any kind of research, there are So numerous papers that correlate positive affect as engaged and negative affect as not engaged, or as like a negative signal. But we should never make this kind of oversimplified assumption that when the person smiles, they are happy and they're having a good experience. And when they are kind of contemplating facial expression, that they are not having a good time and they are frustrated with the robot. That is not true, right? So we ran this like study during the child using the data we collected during children interacting with the robot. We dissected this into different contexts during the interaction, right? Different interaction states. And we filtered and ran correlation analysis on the affect signals. And this is the result. So what you see here is you don't have to worry about blue and red, but look at how the same expression, facial expression, is both on the positive side and the negative side. The positive and negative side is what is like showing is the correlation to the learning outcome. So how successful the interaction was. And you can see that almost every facial expression is on both the positive and both on the negative, right? So sometimes even the surprise, like sadness signals correlate positively to the learning outcome, meaning it wasn't that they are engaged. I mean, if they weren't engaged, they can't produce good interaction outcome, right? But it needs to be really understood based on the context. And we see a high correlation to when we interpret affect signals based on the interaction context, we get much better prediction power on how engaged the child is and how predictive it is for the outcome of interaction. So wrapping up with takeaways. So robots deployed in the real world are to serve, right? Different applications, different roles, but they need to be evaluated on their success of how well they delivered the task outcome and also the human experience. Like how do humans rate their experience and how helpful the robot was. And affect signals can be a good behavioral indicator for real-time human experience evaluation if used correctly. Affect signal understanding, for example, in this case, engagement that I presented on, can benefit from personalized models that adapt to the target users' cues. And we found this this is applicable to many different social cues, based on culture, based on age, based on gender, all different factors. Lastly, please do not make this frequent mistake of using affect signals, treating positive valence signals as good experience and negative valence signals as bad experiences. Interpret it within the context. Thank you.
Hey, Ashish, if there are questions in person, please, you can ask that on the mic, else I can channel the questions that we got virtually and some that I noted down as well.
Any questions for the speaker? So the question is, how can you make sure that the students don't have bad experiences or avoid having bad experiences with the robot?
Well, I don't necessarily think having bad experience is bad, because it's like, yeah, so we had like kids who will just like never respond to the robot, right? They're very reserved. They wouldn't like actually open up or even enjoy the experience, right? That is bound to happen. We are not trying to make 100% happiness, like we are not targeting everyone to be happy with the experience with the robot. But it is, like, bad experience is an experience. Like for those kids, they would have an experience of like interacting with a machine being, right? And that they should have like learned something. They might have learned that, oh, the robots are dumber than I thought, that they don't recognize social cues the way they can, or express cues that they generally do, that they also can't answer their questions all the time. So they will have gained those experiences. So even if they didn't enjoy the moments with the robot, I'm sure they have learned things from the experience, and I wouldn't classify that as a bad experience. But changing like the topic to a more like a daily companion robot, yeah, so we are striving so that people are having good experience over time, right? So some of the strategies we employ there is the notion of relational companionship. So how can we design so that the robot is providing more notions of it being growing over time through the interaction with the user? Because when people get the robot or participate in a study, it is because they're interested, or if they purchase a robot, their initial perception towards the robot must be positive, right? So it's very important to maintain that and showing what the robot is capable of. And I wouldn't say like currently we are doing well on these regards, but those are the aspects that we are striving, because when you actually send robots for studying or actually commercialize robots, unlike you think, I mean, you initially put a lot of effort in the utility of the robot, but people naturally associate character to this physically embodied social things that moves around as like social actors. So a lot of the comments and dissatisfaction actually come from lack of character, lack of personality, lack of companionship. So those are things that we are carefully working on, especially for the daily companions.
Any other questions from the audience? Unnat, are there any questions online? Or
Yeah,
if you have any questions?
Yeah, I can channel some questions here. I think one thing that would be nice to know is some illustrations or examples of what are the knobs that these robots can tune to personalize themselves to a child or to a user. So you gave some examples of engagement, etc. But if you can give us a couple of examples of what are things that the robot can change so as to elicit a better engagement with the user.
Yeah. Great question. So the first layer is like understanding human cues, right? So the last bit of understanding, personalizing for the different engagement cues that different people elicit is one thing. And we have like a different like line of work trying to personalize understanding of the social cues. Second bit is also then personalizing the generation of the robot's intent, emotion, the experience, because people expect that to be be a reciprocal interaction, right? When you're interacting with a social robot, right? So it's also about personalizing the generation of the cues. Like for example, it can include dialogue. So one of the work we are doing is creating relational dialogue that is more related to the topics that users are interested in and have shared with the robot in the past. So how can the robot now learn from that? And next time is conversing with the user, be more on topic, build on the previous interaction, right? The real interesting thing is like through interaction, what the robot learns and is able to adapt. I personally think the robot changing its role and being adaptive of its role and not settling on just one role, which could be always a helpful companion or helpful assistant, but changing its role based on the context, right? And changing the role based on how the user engages in the work that I presented, right? So there's like a layer of how can we personalize the robot's role, also the robot's behavioral personality even over time to match to the users, because it's like so silly if you think about there's like one personality of a robot that can satisfy everyone. We are not built that way. We are very tricky, right? So those are the different layers of personalization that I have attempted at designing and developing algorithms for. And I personally think this line of work is very interesting.
Got it. Yep. Thanks so much. Hey, I think the Ashish, we can thank.
Let's thank Hey again for the wonderful talk.
Thank you.
Yeah. So you're, yeah. We'll get on with our next talk now. So we have Deepak Pathak, who is a faculty in the School of Computer Science at Carnegie Mellon. He's received his PhD from UC Berkeley. His research spans computer vision, machine learning, and robotics. He's a recipient of the faculty awards from Google, Samsung, Sony, Good AI, and graduate fellowship awards from Facebook, NVIDIA, Snapchat. And his research has been featured in many popular press outlets like The Economist, Wall Street Journal, Quanta Magazine, Washington Post, CNET, etc. And Deepak received his bachelor's from IIT Kanpur with a gold medal in computer science. He's also co-founder of Visage Map Inc., which was later acquired by Face First. And he'll be giving his talk that's called Robots That Continuously Improve by Watching and Practicing.
So should I mute myself?
Yeah, you should mute yourself. You can share sound and it will go through here when you share your screen.
What do we share?
So we can
it's already shared.
Oh, the sound is already shared. Oh, I think this. Can you mute this? Yeah. This.
But if I mute here, will the sound?
Yeah, it plays on the Zoom if you share sound.
Okay.
Okay.
Maybe I can quickly try the sound.
Yeah.
Can you hear me? I think it doesn't play.
Keep yourself muted here.
Okay. Okay, sorry, this is different. Okay, hi everyone, and thanks for coming. Hope you are enjoying New Zealand so far. Okay, so what is goal of robot learning? Well, in my opinion, the goal of robot learning is to build robots that can do thousands of tasks in thousands of environments. Not building a robot that can do one thing and one thing only, but building robots that can actually do different things like putting your clothes in drawer, watering your plants. Not in just your house, but every house and every environment out there. Now, this goal is kind of exactly the opposite where things are today in robotics. Like today, we have systems that can do one thing really, really well, like system that can do all sorts of clever parkour tricks on the left, but apparently putting a single block on the table is very difficult. And the failures in robotics are catastrophic, as we see on the right. Now, this generalization is not just a problem in robotics. This is a problem in almost all domains of machine learning. For instance, even in the simplest case of supervised learning, where we know that we can obtain superhuman performance on all these benchmarks like ImageNet, if we transfer these models beyond ImageNet to scenarios like video from YouTube, not very far, they find things like cobra snake, ray fish, flatworm, and completely misclassify even the basic dog example when they are faced with unseen scenarios. Now, this result is still 5-6 years old. It's ResNet 50. Now, who cares about ResNets? There was a talk of the yesterday. Like today, we have transformers. So my students were like, these failures no longer hold true, and we have transformers that work really well. So here is a result for you from 6 years fast forward from VIT, and I pass it this image. What do you think is the output? Well, it's a Band-Aid. Now, you can, if you squint enough, you can say it's like a Johnson & Johnson Band-Aid, but look at the confidence of the model as to how highly it is saying it's a Band-Aid. So this misclassifications and overconfidence are an issue. And this issue is primarily there because of the assumptions we make in machine learning. We always assume that our training set and test set, they belong to same distribution. And whenever these assumptions fail in the real world, things start to fail. Like in robotics, these things fail continuously. Even in vision, like we may train our objects on examples like chair, etc. here, but in real world, when you put on a robot with a camera on top, things look very different. Like chairs may be fallen and your head may be tilted, etc. So the question really boils down to how do we adapt to scenarios? How do we generalize beyond training to these ever-changing situations? And my argument to this talk is that there is only one simple way to do this, is to continuously adapt online. Because we cannot expect that we have seen all possible situations in the future ahead of time. So what I'm doing is I'm arguing against this current paradigm of training once a super powerful omnipotent model which can work in all possible scenarios, which we train and then we deploy it. This is very ambitious and perhaps totally unrealistic. In fact, in nature, it's completely the opposite. This is like saying freezing your brain and expecting you to work all your life. No matter how smart you are by the age of 10, if you don't update your brain and don't learn new things, you cannot function in this changing world. So in nature, things are exactly the opposite. Like the change is incremental, things evolve and continuously happen over time. So how do we formulate this idea of continual adaptation in robotics? So I'll show you some examples through this talk in the context of fixed tasks, and then we'll go to lots of tasks and lots of environments. So let's say you have one robot out there which can walk. So this robot learns to walk in simulation in one setting on the left. It's a bumpy surface. And then you ask it robot to walk in all new scenarios out there, like settings on the right. Now, this is a paper called RMA where this robot is adapting at 10 hertz, which is it is adapting at the rate of milliseconds. And this paper we released a couple of years ago, and we showed some strong results in new settings where the robot was not trained for. For instance, on the left, it is trained only on the bumpy surface, but on the right, on the top left, you can see we are putting it on stairs. It was never even trained for stairs. And the main theme behind this work was how to make robots adapt in real time to new situations. So let me go to the idea a little bit. This is old work, so I'll not spend too much time on this. Now, the idea is you are training this robot to walk in simulation. So you are conditioning it on the state and action pairs. But instead of going and then you want to randomize the environment because you want the robot to transfer to real world diverse situations. But instead of trying to train an invariant policy that works across all these randomizations, like that is the case in domain randomization, you train an adaptive policy, which is aware of the surroundings it is walking on. So you make the policy aware of mass, friction, height, strength. You condition the policy on this such that it can learn to walk. So this policy is aware and not invariant. This is more adaptive and invariant, like in analogy to robust control and adaptive control. In robust control, you want single policy to be robust everywhere, while in adaptive control, you want the policy to figure out the system first and then act in that system. So in the same vein, this is a deep learning analog of adaptive control. Okay. So let's call this vector extrinsics because this is capturing all the information coming from outside the robot, and you're compressing this end to end into a small latent. But how do I deploy this? It's not possible because I don't have this extrinsics at test time in the real world because I don't have all these parameters which I trained on from training time. I don't have the mass, friction, etc. So the idea is in this paper was to estimate these extrinsics online from history of the robot. Okay, so you train another module at training time, which is this adaptation module or RMA module, which looks at the history of the robot to output this latent vector. Now, why should history have any information about encoding of parameters like friction, restitution, mass, etc.? Well, it does not. Look what the history contains. History contains two things. It's not just history of how the robot was, like what robot's own sensory input. It is also history of what was commanded to the robot. So what you are really looking at is disagreement between what you told the robot to do and what it did. So for instance, if I move my hand in air, I apply 1 unit of torque and my hand moves 1 unit. Inside water, for the same torque, my hand will move less. And that discrepancy is caused by the environment I am in. So this discrepancy between what was commanded and what happened actually contains information about the environment you are in. And luckily in this paper, we could train both the systems in simulation. So in phase 1, we train this policy end-to-end through reinforcement learning to obtain this encoding ZT from the environment encoder and base policy. In phase 2, you distill this knowledge into a adaptation module that only regresses the adaptation vector ZT from history of the robot. Now this phase one is reinforcement learning and phase two is supervised learning. You are basically supervising the RMA module to output Z hat T, which you have supervision from the first part. And now this is supervised learning, so you can perform dagger and all those sorts of tricks to distill the information. Okay. But the cool part here is that these two things are completely disentangled. So at test time, I can just take the base policy and the module and put them together at different frequency mismatch. This system is completely asynchronous. The adaptation module can operate at a slower rate because it's performing a more computationally expensive operation. It's processing the history to figure out which environment you are in. Are you on carpet? Are you on snow? Are you on ice? Are you on stairs? And the base policy is just a walking part, it's just the controller, and it is using the latest information available from the module, and which is ZT, and using that to act in the real world. Okay, so this is what happens at test time. Now, one key thing here is that in simulation, when you start an episode, most conditions like terrain, height, friction, they all remain same in the whole episode. But in real world, you can in fact adapt continuously. Even if you leave the robot on, let's say, sand, the exact effective friction or the exact effect of friction that can change continuously depending on where you are, what part of your body is touching the ground and all this. So you can continuously adapt at a very high frequency at test time and not just once in the beginning. And this leads to all these results where we see a robot walking in across all these scenarios trained purely from simulation. To show you some analysis of the system, we put this robot in this terrain, and we put to really analyze, is the robot really adapting, or is it just very robust and an invariant system? So we create this scenario. This was done during COVID time inside home. So we have this environment, we add to this plastic sheet, and then we add oil to the surrounding. So here we are throwing olive oil onto the surface for science. And then we add plastic sheet on the legged robot as well. And then we ask it to walk over the scenario. And you can see it has no trouble walking over this surface, but it's difficult to see in fast. So let's see it in slow motion. And you can see it could walk over this, etc. And then you can also visualize the adaptation happening in real time. So here the same robot is walking over this, and you can see the Z vector, the last column, the last row, Z1 and Z5, they change their behavior in real time as soon as the slippery surface start to appear in front of the robot. So this adaptation from history of the robot is happening online at a real time in a very fast manner. So here is one more example of throwing weight on the robot. So you put the weight, and then you can see the robot bends its knees to account for the impulse coming in from the weight. Now, it was not trained for throwing weights in simulation. This adaptation is actually happening at test time. But then there are many open questions remain. Like so, this paper was 2 years old. So the question remained like, does it scale to more complex robots? Because this is still a pretty low-dimensional robot. It's a legged robot with 4 legs, so 12 motors and 12 joints. Can it scale to more complex systems, like this idea of simulation to real and training and the real-time adaptation? What about beyond locomotion? So it's still walking at a decent speed, but not very fast. Does it scale to more dynamic tasks, more agile tasks, which robotics people care about? All these results so far, by the way, were blind robot. The robot could not see anything in front of it. So it was trying to adapt by using its legs as sensor. So like you use, like blind people use stick to find the terrain and then walk over it, the robot was using its leg and proprioception to adapt to all these scenarios. But can this adapt in real time from higher dimensional input like vision? And finally, how do I go to this original goal of lots of tasks and lots of environment? So in this talk, I'll show you some examples of these open questions that we have been working on. So first of all, on this problem of going to more complex robots beyond locomotion, because locomotion is very restrictive, we add this arm on top of this legged robot. This is deep whole body control. This is also presented in this paper, in this conference in more details. And here the idea is we want to go to a more complex system, which can not only perform locomotion, but also perform manipulation altogether. Now, there are many platforms out there, but not quite affordable in academia. And probably most of you can understand what I mean, because these robots cost over 100K to buy just one unit. And if they fail or if they break, you are out of budget for next few years. So here we build our custom built lightweight manipulator, which is very cheap, costs $5,000, $6,000. And so it costs 11K, but you can actually build it in 6,000. And because this robot is $3,000 without software. And you can see everything is low cost about it. Now, what does low cost mean? Low cost means motors are noisy, not quite repeatable, and not very precise. This is what low cost means. But that's okay because we are using learning here. The challenges in such a problem statement is that it is very high dimensional. Now, suddenly you are no longer caring about one task of walking, but you also have manipulation, etc. So there's local minima because arms would like the robot to not move because that's more stable to perform manipulation. Legs would not like arm to move because that's most stable for walking. So they kind of are opposite against each other. So the classic approach is to address this whole body control is to train a separate system for manipulation, separate system for locomotion. And then if you have time, you train another system or like not a system, you optimize something together to put these two modules together. This is very modular approach people follow. Now, can we apply or extend the same similar ideas to this whole body control problem over here? So one straightforward thing first we thought, okay, can we just apply the previous RMA idea in this high dimensional setting? And turns out not quite, because we made one assumption while in the previous algorithm. The assumption we made is that compression implies predictability, which is not true. Because in phase one, I'm compressing this privileged information into a vector ZT, and which is used for walking. I'm just hoping that the same latent representation can also be regressed from history of the robot at test time, which is not true because there can be multiple solutions. But there is an easy fix to this problem. What we do is we regularized the phase one training to be predictable. At the same time, it is compressing the latent. So you merge the two phases into one, and the first phase takes the privileged data and outputs some latent representation, which is used for training the policy. At the same time, you're making sure that the same latent also has low error when you're trying to regress from history of the robot. And history contains both what you commanded and what happened. Okay, this is the system we use for whole body control of this setup. And with this one change, we are able to, and plus one more change on advantage mixing about the reward toward local minima. With these two changes, we are able to put this system on this whole body control setup. Now, Zoom is causing a lag. This is not live screen. But if you notice, human is only commanding where the end effector of the arm should go, and the whole body is adjusting for it accordingly. Like the legs can bend when the arm goes down, the body can roll. Maybe it's very difficult to hard code and optimize for every possible situation. Where here a single network is able to do the whole task for you, and you only specify where the end of the arm should go, and the whole body accounts for it automatically. We also have brought the same robot to here in CoRL for live demos, and we haven't tried it yet because we just got it here yesterday. If the robot is all right through the plane journey, so we'll show it in live at some point outside. Okay, what about beyond locomotion? What about more agile tasks? So for instance, like legs are not only used for locomotion, like dogs can do all sort of tricks, like they can climb doors, can open doors, can climb walls. And in the same spirit, we wanted our robot to do something like same. So here we train a robot using similar approach, which is this regularized online adaptation for training the robot to climb on the wall. So this task is much more dynamic than walking or running. So here, this robot now will try to climb the wall and then balance on the wall using 3 legs, which is again very hard because the body is not quite made for such kind of task. And then have it come down. A lot of lag in the video, but let's still see in slow motion. So you can see the robot actually is trying in the air multiple times to create momentum to climb, and similarly to diffuse the momentum while coming down. So this is a very dynamic task in that sense. Okay, and beyond quadrupeds, we've also scaled a similar idea to biped robots. So here's Cassie robot, and similar oily surface example. But now this is biped, much more costly, like 300K or something. So we cannot really leave it unhinged. So we have this slacked rope on top just in case things go haywire, because we cannot afford to lose this robot, especially because it was not ours. Okay, so far, one thing that the common theme across these works is that everything was happening from body sensing, like from proprioception. And the reason for that is proprioception is very low dimension. All I observe is my joint angles and that's it. But it's very limiting, right? And although it led to good results, like it was pretty effective, but ideally we need vision. But why do we need vision? Well, vision is required to walk and traverse terrains which are very difficult to do blind. For instance, climbing stairs, going on the stepping stones. This is very difficult if you cannot see what is in front of you. So I showed result of robot going down, but did not show results of robot going up because that requires you to see at least the first time when you go to the stair, then you can repeat the pattern, right? So, but how do we use vision? So let's take a step back and see what is the traditional way of using vision in robotics. In robotics, we usually treat vision as second-class citizen to control. So we use vision to build map and we throw away the vision part. And then we operate on this abstracted map to build policies, right? Now maps are useful if you have to go from here to Starbucks. You use Google Maps all the time to figure out where to go. But do you remember how many stairs are there from here to your office on your way? Or how many stairs are there on this thing if you have walked this thing even once? You don't, because we don't build maps at this high frequency, at this such a low level control, because such maps are extremely noisy. So you can see the examples on the left, like your robot is building this map at very high frequency, and look at the amount of noise on a regularized stair pattern. This is very high, right? And this is why what people do is that to account for this noise, you add noise to the controller during training, which hampers the performance. But this is the only way to work in noisy maps at test time. How do humans get around this? Well, in humans, control and perception are tightly coupled together. So this is one of my favorite experiments on kids. This is an experiment from 1980s from David Lee, trying to show that how vision and control are tightly coupled in humans. So they on kids when they learn locomotion. So here, what David Lee does, he puts a child in this room where the walls are moving, and walls can be moved. Now, the child sees the walls moving and she falls. She doesn't even touch the wall. Just the fact that the vision system gets confused completely confuses the control part, and the robot just not the robot, the kid the kid just falls over there. And there are many such experiments in the last 40 years trying to show this reliably, repeatedly across setups, across kids from different parts of the world. This is an established thing that vision and control are tightly coupled, and when control evolves over time, vision has to be relearned. It's not a module that you can just transfer. This is a known thing. So in this paper, which is also in CoRL, we try to put vision as first-class citizen in control. So which means that we directly operate from visual input. So here in this robot sees this image as input on the top right and uses that to directly output the command file motor. There is no mapping or no footstep planning in between. It's directly from vision to control. And this is why it is able to do this fine-grained task, like walking on these stepping stones. It can cross over gaps, go down, is going all these difficult stairs. Notice the height of the stair and height of the robot. They're almost the same. So this is not like humans climbing stairs. This is more like humans climbing hurdles for this robot. It's a very small, low-height robot and low cost. The way it figured out how to go around stairs, because it learned this gate where it puts the legs outward. Like when you climb a wall, use the leg to put on the wall first and then you climb. So it learned that gate, and we never predefined any notion of gate in this setting. Okay, so all these results were from a single egocentric camera in front, no mapping, So it was map free and no gating. So it was gate free. Okay. And this gate free nature allowed it to work despite being very small compared to other robots out there, which can just fold their legs to climb on something. This small robot cannot do that. So it learned this abduction adduction behavior of extending the legs sideways outwards to account for these high obstacles, despite being very small. And here are other challenging scenarios. We have given live demos of this robot. So we also have this robot as well here. So we got like multiple robots from US to New Zealand on a long flight. We'll give these demos, but we have found one issue that our camera got damaged. So we are trying to put on a new camera while being here on top of the robot, and let's see if it works out with a new camera placement, which is like changing your eye location inside your body because there is no mapping. It's a direct sensing from the camera. So location of camera matters. Like if you change your eye, you cannot adapt immediately. You need time. And this was during the New Orleans Mardi Gras party. So people were more interested in the robot than in the Mardi Gras presenters. How do we scale the system to lots of tasks in lots of environments? I'll quickly give some brief glimpse of this. This was so far on one task, walking. We did lots of environments, but kept the task fixed. How do we scale the system to lots and tasks in lots of scenarios? Because for lots of tasks, like one way is to build simulator for everything, which is not very scalable to create every single kitchen, every single living room out there in simulation. It's a very difficult task. Second, if we don't do that, we don't have data to train for robotics, unlike vision or language, where we have images and text out there. So how do we go around this? So this causes robotics to face this chicken and egg problem. So in robotics, we don't have robot data because robots are not deployed. They are not deployed because they don't work. They don't work because there is no data. So this is a loop. What comes first? Data comes first or the robots come first? And this is where we are stuck at. So what we propose as a way out of this problem is by using the only robot out there which functions every day throughout like 24/7 across the world. And that robot is basically human. Like there's a lot of data on YouTube, on internet of humans acting in the world and doing things. And we would like to use that data to understand priors to bootstrap robotics at the first place. Note, I'm not mentioning imitation learning. Like imitation learning or imitation in robotics, that when we say it, it's usually meant this, like where somebody controls a robot either through VR or by holding it to give exact commands in the robot section space. I'm talking about learning from observation, learning by watching, where you watch someone do something and then you repeat it on your own and then you get better at this. This kind of learning happens in humans all the time. And this is the reason we can learn from others, even when they are not teaching us. So the idea here, but there are many challenges in doing so. Like humans have different body than robots. And second, just watching is not enough because that doesn't tell me about forces, contexts, where should I touch, how should I actuate my fingers. So this is a lot more challenging than just performing imitation learning in this setting. So our idea here is that we use videos on YouTube to basically understand priors of how to act, what to act, where to act in the environment, and use that priors to initialize robots, and then actually practice around those priors in real world using some exploration or something to improve the policy. So to give an example, like a human comes and let's say does a video of opening a drawer. Now you can, from having seen lots of humans out there, you know where the hand went, where the door opened, and then you practice in the real world to improve yourself. And in the beginning, you can see the robot was not able to open the drawer, but after practicing in the real world for 1 to 2 hours, it can go and open the drawer. So this is training without requiring any simulator, etc. So this basically involves extracting prior, then exploration, and then repeating this in loop continuously for a few hours. The only thing you need here is to really know how much progress have you made, because you cannot compare human videos to robot videos. So we did a simple trick here. We in-paint the human out, we in-paint the robot out, and we only compare the environment that they affect to know whether robot is succeeding or not. So we use in-painting to compare the video without presence of humans in there. Okay, so here is the result. So this is training without using any simulator, no reward function design. You can think of this approach as basically a zeroth order policy learning, where it watches the person, practices, improves, trying to get its environment to look the same as in case of humans. So we could scale this very quickly across tasks, like it takes few hours per task, and we see improvement as we increase the number of iterations in the real world. But the main thing is, for training a single task, it required essentially like a few hours of effort. So we were able to scale this very quickly to lots of tasks and lots of environments across CMU. So here we are showing pretty much every kitchen and every living room in the CMU CS building, because it was snowing out in Pittsburgh. So we could not take the robot outside. And all these experiments were done inside, like in the office environments. We have also trying similar effort on dexterous manipulation. So for instance, to get the videos on YouTube, and then now this is slightly easier because if you have a robot hand, you can actually directly map human hand to robot hand and transfer the knowledge. So here is a live training going on. The images are the frames from YouTube videos. And on the right, the human hand is being aligned with the robot hand as the training goes on. And as it goes on and on, the alignment starts to improve by only using data from YouTube, not using any data from robot. So here is a demonstration of that. So this system trained purely on YouTube can now be used to control robots through what we call robotic telekinesis. No gloves, no VR, just a single camera. We also have results from a Zoom call because it only requires an RGB image of the person doing RGB video of the person doing something and transfer it to robot in the real time. But this is not enough to get the policy. So what we do, we train 1 or 2 demonstrations we collect 1 to 5 demonstrations in the real world, very few number compared to the number of YouTube videos. And then we just train a policy to directly control these things in the real world. So this system was trained on 200-300 videos from YouTube and 1 to 5 examples from robot data. And this is testing on unseen objects. It was not trained on any of these objects at training time for these tasks. Okay. So just to summarize, the high level thing we have seen so far is that we can extract these video priors from YouTube and then improve around them by exploration in the real world. And then once we have a policy, we can we are still to combine the adaptation piece to adapt to new scenarios and new situations at test time. Okay, so this is still an open problem in robotics, which is building the general purpose skills. YouTube provides a lot of interaction data to begin with, but just watching is not enough. You need to also practice to improve the robots in there. So most of these works were done by the students here, like Shikhar, who did the work, all the work on manipulation and learning in the wild. Ashish and Ananya, they worked on the legged robot and all the cool results you see, and they'll be giving demos throughout the conference as well. And I'm just a mouthpiece for all these students out there. Thank you.
We're running slightly behind, so maybe we have time for one or two questions. The audience has some.
Correct. So then in that case, you are essentially relying on the robustness. So like, for instance, in this setup, like not everything you are doing, this latent is capturing. Like for instance, I may not know what is the exact friction of this carpet or what if there is a particle on the carpet or not. Like there are some things I'm robust to, other things I adapt myself to. Like I will not walk very slowly on this like I walk on snow or oil. I'll adapt my gait, but then I have to be robust to still very, very small particles in there, which may cause me to slip. So it's a combination of both. So it's like whatever parameters you put in the vector, we learn it, and then it gets compressed into a latent. And then you try to regress that latent from the history of the robot. Now, it may not always be regressible, where I showed this other example, where you can also regularize this together to make sure it is regressible in an end-to-end manner. Okay. Thank you.
Yeah, I think we have to move to the spotlight session, but thank you so much, Deepak, for the great presentation.
Thank you.
So next we have our second set of spotlight presentations. So the first will be planning goals for exploration given by Edward. Yeah. And so you joined the Zoom, so you could just share your screen and then mute yourself, and then you can put audio as well.
All right. Hi, everybody. I'm Edward Hoob, and I'll be presenting planning goals for exploration. This is joint work with Richard Chang, Oleg Rybkin, and Dinesh Jairam. So our work is motivated by the setting of unsupervised task discovery. In it, we drop an agent into an unknown environment. For example, we may drop a household robot into the kitchen. We start with the exploration phase, which is we figure out what can be done in the environment and how to do it. Afterwards, we proceed to the evaluation phase, which is you just set an arbitrary new task in the environment for the robot to achieve. So maybe that we want the household robot to first, play with the kitchen utensils, open some drawers, and in general, learn the affordances of the kitchen during the exploration phase. And then the next day, we ask it to set up the countertop. So it's clear that the more diverse exploration experience the robot gathers in this exploration phase, the wider variety of skills the robot can learn from that data set. And in general, it can become a more generalist agent, right? Oops. So let's talk about task discovery in goal conditioned RL though. So in goal conditioned RL, we train an agent policy pi of g conditioned on not only S, but goal variable g to reach any specified goal g. And in GCRL, a common way to explore is through something called Go Explore. So in Go Explore, what we do is we set a goal G. So like in this example, we're going to set this goal star G, and we're going to execute the goal condition policy condition on this goal candidate. And then we're going to end up in some terminal state S of t. Then at S of t, we're going to launch an exploration policy. And this is all done in the same episode. We record this full trajectory in the data set D, and we improve the goal condition policy on the updated data set, and we repeat this until convergence. So we didn't talk about how to actually choose a goal for Go Explore. And it's clear that we should intuitively set diverse goals, right? Because we want to collect that diverse experience that I mentioned before. But how do we reason about the reachability of these diverse goals? Or what about plausibility? So like basically this idea of a diverse goal is kind of ill-founded so far. So this leaves open the question of how should an agent choose goals to maximize exploration? So we aim to answer this in our work, and our key insight is to optimize for the exploration rewards gathered by the exploration policy pi of e. So pictorially, what this means is inside this red circle, when we choose goal candidates like these stars, we want to choose them such that the resulting terminal state of the goal condition policy conditioned on that goal is a good initial state for the exploration policy to roll out from. So in math terms, what this means is we want to maximize the goal variable G. And what we're going to do is we're going to reason about the conditional distribution of terminal states of the policy conditioned on G. And we're going to measure how much exploration value we can get from rolling out the exploration policy. In order to actually optimize this objective, we need to foresee where the goal condition policy will end up conditioned on some goal variable G, right? So we're going to learn a world model to do this. So now I'm going to dive into the details of our method, planning explore two goals, or PEG for short. In step one, we're going to sample goal candidates from the state space. So you can see I have like these stars to represent them. And then what we're going to do is for each goal candidate, we're going to use a world model to predict how the goal condition policy will act when conditioned on these goal candidates. So maybe for the orange star, we're going to roll it out in imagination. So the world model predicts that it's going to end up at this terminal state. And we're going to do the same for the other goal candidate. It's going to end up at this state. And so once we've done this for each goal candidate, what we can do is start scoring them by the exploration value of the terminal state. So what this means is like zooming in on the purple terminal state here for that purple goal, we're going to evaluate the exploration value function, which just says how much expected future reward will I get from rolling out the exploration policy, right? So we can see just in this scenario, the value function thinks that we're going to do pretty well in exploration, and we're going to do it for every terminal state. So for this other terminal state induced by the other goal, the value function thinks it's going to do pretty poorly. So we simply just choose the best goal, the one with the highest value for Go Explore exploration in the real world. So zooming out a little, like this is the actual training loop of our agent. What we do is at the start of each episode, we're going to generate a goal using the objective I just described. We're going to use that goal for Go Explore exploration in the real world. We're going to record an exploration episode in the replay buffer. And then finally, do an improvement step with model-based RL, where on this updated data set, we improve the world model, the policies, and the value functions. With the updated world model and the policies and value functions, we actually improve the PEG goal generation itself. So this is kind of a positive feedback loop. Now I'm going to dive into the experiments. So we have environments ranging from like maze navigation to locomotion to our hardest one, which is block stacking. Really quickly, how it works is we're going to drop the agent into each environment, train it with this unsupervised acceleration algorithm, and periodically evaluate a goal condition policy trained on that data to reach hard acceleration goals. So yeah, so what that means is like maybe for the point maze, the hardest goal is like this star in the top right if you were starting in the bottom left, or for block stacking, it would be to ask the agent to stack 3 blocks, which is something like hard to discover from pure unsupervised exploration, right? And what you just find across the board is that PEG, which is our blue line, outperforms like other goal setting baselines and non-goal setting exploration baselines. And the performance increase is especially apparent in like the hardest environment, which is block stacking. So we're going to focus on block stacking. And what I'm showing you right now is the evaluation episodes of the goal condition policy. So what we see is basically the goal condition policy is able to stack 3 blocks because our exploration is sufficient. So it's able to discover like pushing, poking, pick and place, and in general, stacking the blocks, all from no supervision. And that diverse data set is what enables us to learn this performant goal condition policy that can execute the 3 block stacks. And let's actually see what's happening in the exploration episodes. So note that this yellow orb is actually the robot. We just made it invisible for visualization, but actually it's a robot. So what we see is like a very interesting exploration behavior induced by our method. So what happens is actually PEG chooses goals such that the robot stacks the blocks first. And then once it makes a stack, it switches to the exploration policy, which elects to throw out the blocks out of the workspace to maximize the exploration. So yeah, it's pretty cool because I think this is a pretty sophisticated exploration behavior that I was not expecting. So in conclusion, we have PEG, a model-based approach for goal setting to train goal-conditioned RL agents to become generalists in a novel environment and with no supervision. So you can check out our website for like more GIFs and results. And just some future work is we could use PEG to like maximize reward metrics for like task relevant exploration instead of just like assuming some unsupervised exploration reward. And we can also do more long horizon exploration if we use temporally abstracted world models instead of just one-step world models. Thank you.
We'll take, thanks for the talk, Edward. We'll take maybe one question from the audience. If anybody has questions. Yes. When you say world models, is this world model from pixels?
So in our work, we do from states. Yeah, but it definitely is a future work to do world models from pixels. And one way you could do this is learn like a latent representation and then do like the goal planning in the latent space. Yeah. And we build on top of like Lexa and Panda Explore, which have originally been shown to work with pixels. So that's definitely an open work. Yeah.
Cool. So I think we'll get started on the next presentation, which is pre-training for robots. Offline RL enables learning new tasks from a handful of trials. And the presenter is Aviral Kumar from Berkeley. Can you share your screen? And could you unmute him, Ben?
Yeah, can you all hear me? And can you see my screen?
Yeah.
Yeah, okay, great. Yeah, so hello everyone. Today I'll talk about pre-training for robots, how offline RL enables learning new tasks from a handful of trials. This is joint work with Aniket Singh, Frederick Ebert, Yanlai Yang, Chelsea Finn, and Sergey Levin. Okay, so yeah, so our vision in this work is to be able to incorporate large and diverse robot data sets into training pipelines for robot learning systems. So imagine something like you have a broad diverse robot data set collected from labs all over the world. You potentially want to extract some kind of initialization from this data such that when I now want to solve a given new task on my robot in my lab, I can potentially collect limited amounts of task-specific data and adapt or fine-tune this initialization on that data to get a policy that can solve this task and also generalize well. So that's our vision. And the question that this entails is how can we learn from these large robot data sets? So if you look at how prior work has approached this problem, it has often approached this problem in this two-phase training paradigm, where you would take this broad data, you would run some kind of pre-training on this data. For instance, one common technique to do this is to extract some kind of representations or visual features that can allow me to learn about objects in the world and so on. followed by some kind of adaptation or fine tuning on limited amounts of task specific data. For instance, you could take this representation that you learned, and then you learn a little small policy, neural network policy on top of this representation. If you look at prior works, here are some of them. Certainly I missed many of them, but some of them are here. They often follow this paradigm of visual or computer vision based representation learning, followed by imitation for fine tuning on the task specific data. In contrast to these works, what we'll ask in this talk is, can we instead use offline reinforcement learning as a way for doing both pre-training and fine-tuning? And at first, this might sound like a very strange question because, when you think of pre-training, you think of learning some representations, and computer vision techniques already give us good representations in principle. And when we think of adaptation, we think of typically imitating, let's say, a human demonstrator or so on, and we think of imitation learning. So why offline RL in the first place? And I would argue that in some ways, offline RL or reinforcement learning in general provides us with a general paradigm to extract control-centric representations that are in principle the things that we want to extract from this driver's data set. Because at the end, we want to train a policy to control my robot. And what is a better representation to do that than a representation that can make me aware of my future actions, right? Or the outcomes of my future actions. And that's precisely what RL should give you. So therefore, we should use RL for both pre-training and fine-tuning. So how can you do this, right? How can you instantiate RL for pre-training and fine-tuning? And that's exactly what our work tries to do, which is it proposes a robotic system that can use offline reinforcement learning methods out there, puts them into a system to get such good, to get a robotic system that can enable this. So we build on, so for our training, we utilize this data set called the Bridge data set, which consists of a VidOX robot interacting with a variety of objects in toy kitchen scenarios. It was collected across a bunch of institutions, and it has trajectories showing a variety of domains, a variety of objects, variety of tasks, and so on. What we do is we take these trajectories, label them with one hot task identifiers, which is easy to do for this data set, and simply run for our pre-training phase, simply run end-to-end offline reinforcement learning directly from vision in this case. In this case, we use the conservative Q-learning or CQL algorithm. Now, when you are given limited amounts of task-specific data, that is, you want to fine-tune your initialization, what you can do is you can simply continue training the same offline RL algorithm with basically the same hyperparameters, but on batches that are now constructed with a mixture of the pre-training data and the target data. So you can construct a batch which is a mixture of them and continue running the same algorithm. And turns out that if you instantiate this paradigm properly, basically this kind of works as a good pre-training and fine-tuning method that outperforms a variety of prior methods. So what's the new thing here, you might ask, right? And so the new thing here was some details on how do you actually get the architecture for training value functions, training policies. So I'm not going to go into this in a lot of detail, but I'll give you some brief brief points of the key points of our architecture. So we first of all utilize big ResNets, which are modified to use group normalization and slightly wider feature maps. Typically when you think about ResNets and supervised learning, you think about taking the output feature map of the ResNet and collapsing them along the spatial dimensions. That's called global mean pooling in supervised learning. But in control, you typically want to be aware of the positions of different objects in the image. So for accounting for those positions, we kind of learn, we inspired from transformers, we sort of learn position embeddings, which are multiplied pointwise to the ResNet feature map before collapsing them into a feed forward, before collapsing them into a straight flattened vector for passing it into the feed forward layer. And finally, the third thing that we do is we duplicate the action vector when modeling the value function, the value function Q of S comma A at all layers of this feed forward stack. And this was needed because typically, when you take data which is collected using human teleoperation, which is what our data set was collected using, you would have a lot of correlation between states and actions. And to make sure that your learning algorithm can figure out, what's the effect of an action versus what's just the effect of the state, you need to kind of make sure that the action vector is passed strongly enough into the network. And that's why this duplication trick worked pretty well. Okay, so now I'm going to show you some behaviors of our method. So here's a task where, for instance, we want to learn to solve this new door, this new microwave door. We only have 10 demonstrations for this task. We want to solve this end-to-end from vision, but we have data from many other tasks, many other doors in our pre-training data set. Turns out that the best prior method in this case, which is based out of imitation learning, actually ends up hitting the wall of the door, and so kind of doesn't go around the door to open it very well. But our approach, which is PTR, pre-training for robots, it actually ends up solving this task pretty well. There are also other tasks we tried on, such as pick and place tasks, where again you have like a new visual scene, new objects, and you want to be able to like solve them. You only have 10 demonstrations for this new task that you care about, but a lot of pre-training data. Again, turns out that the best prior methods based on imitation often fail to precisely grasp the object or place it in the right way. But turns out that again, PTR performs much better in this case. And I would like to also say that while these tasks do appear simple, you have to do this with very few demonstrations in this case, which is really hard for any method. We tried actually a variety of methods. So here are some quantitative results for our approach. So we compared, so here are some of the tasks. This is not all the tasks, but we compared our approach PTR to a variety of methods which use imitation for fine-tuning, including some state-of-the-art methods which use transformers and autoregressive policies. And we find that actually our offline RL-based approach does give rise to better results, which means it's better at fine-tuning. We also compare it to using representations which are learned from like internet data or also trained on bridge data using state-of-the-art methods such as masked autoencoders. But again, turns out that PTR outperforms these approaches. So sort of the high level takeaway from these quantitative results was that offline RL can give you better representations and better fine tuning. We also show that our method actually ends up scaling much better. So if you use models with higher capacity, you get better benefits, which kind of is very promising because at this point, the larger the network, the better the performance it is. And that's what kind of replicates the trend that we're seeing in natural language processing and computer vision. And finally, we also try to do some focused analysis on figuring out why actually RL enables better performance, even though you have human teleoperation data, which is sort of narrow in its coverage. And I'm not going to go into this in too much detail, but the key answer is essentially when you train a value function via reinforcement learning, it can help you prioritize on decisions that are more critical, more crucial for the learned policy to take. For instance, the grasping action, which you need to take more carefully than just the actions that you take to go towards the object. And these are precisely the failure modes for like imitation style methods, which RL can then correct, which is quite good. So that's basically it. The main takeaway I would like you to take is that offline RL can be, we think of this as a method for control, but it's actually also a method for representation learning. And it can work pretty well even if you have human demonstration data only. There are many future works such as different ways of goal specification, incorporating multimodal data, and so on. And you should definitely check out the paper and the code, which can be found at this QR code. Thank you so much.
Yeah, thank you so much, Aviral. Yeah, we'll take some questions from the audience, and I'll just repeat them if anybody has any. Yeah. Wondering, like, what was the lower limit of the number of demonstrations needed for the fine-tuning? Yeah, I can just repeat the question. So what was the lower limit on the number of demonstrations needed for the fine-tuning?
Yeah, that's a great question. So we haven't done a lot of ablations on this. I can tell you some preliminary results on this. So the paper that we built off of, the one that uses imitation on bridge data, used 25 or so. We utilized 10, which we never really updated a lot, but we just utilized 10 because it was kind of easy to get 10 demonstrations in 10 minutes. In some results that we had after doing this work, we found that you can, on some of the tasks like the door task where you have to go around the door to open it, you can get reasonable performance, the pretty much similar performance with even 5 demonstrations. So I would say that, yeah, I think, at least in some tasks, just 5 also work. I don't know whether things below it don't work, but we have gone up till 5 and that works pretty reasonably.
Yeah, thank you so much, Aviral. Just in the interest of time, we'll get to the next speaker, which is Katie, who's presenting leveraging haptic feedback to improve data quality and quantity for deep imitation learning models. So yeah, let's get started on this.
There was a little bit of lag. Good morning, everyone. My name is Katie Kwan. I'm a 5th-year PhD candidate in mechanical engineering at Stanford. And today I'm going to be presenting my work in collaboration with my advisor, Allison Okamura, and Mohi Kansari. This is a joint collaboration between the CHARM Lab at Stanford and Everyday Robots. The title of our paper is Leveraging Haptic Feedback to Improve Data Quality and Quantity for Deep Imitation Learning Models. Yes. It is a little dark. What is happening? I'm on presenter view. How do we feel? Lighter. Okay, we've come to the light. So we're beginning to see increasingly autonomous robots deployed in various unstructured contexts: homes, grocery stores, hospitals, etc. Here are a couple of examples in varying degrees of finalization from TRI, Badger Technologies, Boston Dynamics, and Cobalt Robotics. Right now, many of these robots have a limited range of tasks, like notifying staffs of spills, for example, but those robots with manipulators should be able to learn new tasks quickly from anyone on the fly in the real world. At Everyday Robots, we use learning from demonstration to teach a robot to open many different kinds of office doors autonomously, latched and push doors. We use learning from demonstration because it's a proven effective method to quickly teach a robot new manipulation tasks. And of course, one of the benefits of learning from demonstration is you might not require conventional programming skills or knowledge of robot kinematics on the part of the demonstrator, i.e. the human teacher. So when we're in circumstances like I described a second ago, we're in situ, the robot's already in the environment, we want to be able to learn from anyone. The performance of the autonomous robot can be upper bounded by the human teacher's performance. And so one open problem in learning from demonstration is how do we optimize human teacher performance? Data quality and quantity play a critical role in learning from demonstration trained model performance. And so in this paper, we analyze the effect of enhancing an existing teleoperation data collection system with real-time haptic feedback. And we observe improvements in the collected data throughput and its quality for model training. In our problem formulation, a teleoperator attempts to teach a robot how to open a latch door. We use this manipulation task so that forces are generated at the end effector because we're contacting the environment. The robot in use is a 7 degree of freedom robot with a mobile base and a camera in the head, also known as the first-person camera. The teleoperator collects door opening examples by standing behind this real robot, so they're co-located, and using a virtual reality controller to open the door. The teleoperator automatically marks this task a success or failure after completing the episode, and all the teleoperators participate in a 1-hour training prior to starting this task. Several teleoperators had performed this task for many hours previously, and we do the teleoperation control by mapping the device controller 3D pose to the robot's gripper in Cartesian space, and then performing inverse kinematics to get the robot joint angles. The robot sends messages back to the virtual reality controller at a rate of 10 Hertz. Once the expert demonstrations are collected, we do behavior cloning and train an image-based model. This probabilistic and transition model is used to learn a robot policy that imitates the expert policy. We use RGB images from the head-mounted camera that were recorded as input to our model. The action space is 7-dimensional, comprised of the arm motion and also a terminate action. So we follow this approach where we use a sort of visual deep imitation learning model to train policies based off of Resident 18. We actually don't feed any of the force information that we record as input into the model. So we collect 2 different teleoperation data sets that vary on this single dimension. In one data set, the teleoperators perform the regular teleoperation task and no haptic feedback whatsoever. And in the second data set, they do get haptic feedback. So while they're performing teleoperation, they're getting haptic feedback for all force torque sensor values over 2 newtons. We provide a proportional amplitude and duration that's linearly proportional to the force magnitude that's detected by the custom 6-axis force torque sensor in the wrist. And this haptic feedback experience was tuned extensively by myself and a couple of other researchers who participated in the teleoperation before we deployed this on the real robot. We had 9 demonstrators collect data on 2 doors of each side, 2 left swing doors and 2 right swing doors. After we collect all of this data, the data was curated to be used for training. We removed all of the failures as well as outstanding poor performers. We also removed mislabeled episodes. And then this data was used to train 6 models in simulation, 3 haptics models and 3 no haptics models. You can read them all in this beautiful list here, but we've got haptics on right swing data, haptics with left swing data, haptics model with a combination of right and left swing data, and then the same 3 counterparts for no haptics. We then test, we train for 20,000 steps. We extract 34 checkpoints from each of these trainings. And then we test all of these 34 checkpoints on 2 doors in simulation. And we take the highest performing checkpoints from each of these 6 models in simulation. And those are the checkpoints that we use for testing in the real world. And then when we test in the real world, we test on both the doors that we saw during training and also a couple of new doors that we've never seen before. We also mark an episode of success if the robot's no longer in contact with the door is successfully unlatched, and the episode duration is under a specific time threshold. So what did we discover from all of this hard work? The results from this process show several important findings. The first is that haptic feedback improves demonstrator performance in the data collection phase. So while the teleoperators are actually going and collecting data, we see an improvement in demonstrator performance by 10%, which is statistically significant. And the demonstrator takes less time to perform the task with haptic feedback than without haptic feedback. In addition, we observe that haptic feedback improves data throughput, which is also statistically significant, meaning more of the haptics data remained after performing curation than the no haptics data. We then show the results from the real world policy testing that haptics and no haptics policies trained on right swing doors pretty much performed the same. So we didn't see a big difference between these two. But we did see a big difference between haptics and no haptics policies that were trained on left swing door data. This task was significantly harder because the robot is a right-handed robot. All of the demonstrators were right-handed demonstrators. And so it's a lot harder to open left swing doors than it is to open right swing doors. And we also see that the policy that was trained with the haptics data on a combination of right and left swing doors also performed better if it had the haptics data. So not only, in conclusion, do we see that haptic feedback improves teleoperator performance during data collection with this higher success rate and a faster average example duration, we also see it improves the data throughput, and then the resulting autonomous policies with the haptic feedback data sets lead to better autonomous robot performance. Thank you so much. I'd love to answer questions.
Actually, I have a question.
Mm-hmm.
Maybe one and a half questions. So I really like from the fact that we're exploring how to improve the demonstration collection itself with haptic feedback.
Mm-hmm.
How easy would it be to kind of incorporate the system with like any joystick, like like that a front with the joystick, or some console, remote. What would be kind of what would bridge this?
Great question. So one thing we're working on now is using a gamepad controller. So all of my gamers out here, and we're also mapping the force values to the amplitude that we get in the actuators inside of this gamepad controller. And we're going to see if we observe a similar effect. So we're going to see if we're sort of device agnostic. But I think it's definitely feasible. As long as you're performing a task that's generating forces that can be read by the robot and would be useful to the human, then you can create a nice haptic mapping between what the robot's detecting and what people are feeling in their hands.
And just one last question. So right now, like the haptic, if you were to deploy this online, right now, like if I understand correctly, it's being used by the imitation models. But let's say we train a policy that has, did not train haptic data, can you use the same kind of technique that you did with the human demonstrator to, with the policy, the online policy awareness?
Are you saying I would like feed my force values that I'm detecting?
Yeah.
Okay. Yes, so we've also definitely thought about that for future work. I think in that case, the state space is a lot bigger, right? So you have images and you need all these different combinations of forces that you detected and the images at the same time. But it's definitely something we're thinking about. Yeah, great suggestion.
Thank you so much.
Thanks.
Yeah, so just since we're out of time already, we have to get to the next speaker. Would you mind unmuting Angela? Would you mind sharing your screen as well? Yeah.
Great. So our next invited speaker is Angela Schillig. Angela is a professor for robotics and artificial intelligence at the Technical University of Munich. She's also an associate professor at the University of Toronto and a faculty member of the Vector Institute. Her goal is to enhance the performance, safety, and autonomy of robots by enabling them to learn from past experiments and from each other. In Canada, she has held a Canada Research Chair in Machine Learning for Robotics and Control and a Canada CFAR Chair in AI, and has been a principal investigator for the NSERC Canadian Robotics Network. Thank you. Take it away, Angela.
I don't think we can hear you.
I'll try a different microphone. Can you hear me now?
Yeah.
Okay. Okay. And you can see my slides?
Yeah, we can.
Okay, great. Okay, thank you. Thanks for the feedback. So welcome everybody. I'm joining from Munich and didn't make my way to New Zealand. I hope you enjoy the conference. I really like to thank the organizers for this work, who organized this workshop, because learning and adapting in the real world is something that basically, followed me since I started with machine learning for robotics. So my talk today is about safe robot learning in the real world. And the motivation for this is clear. The next generation of robots will rely on machine learning in one way or another. It may be that we train these robots ahead of time, or that we learn online in the real world. But we need machine learning to understand complex environments, complex robot dynamics, to perform complex tasks, and to interact with the world in general. However, when machine learning algorithms or their results are deployed on robots in the real world, the safety is really important. And that's something I'd like to emphasize in this talk today. And to set the stage, I'd like to take you to my lab. And I hope you can see this okay. So our goal in my lab is to achieve high performance motions with teams of robots. And we continuously test our algorithms on real robots. So here you see 25 vehicles flying in close formation. But we've also taken these vehicles outside of the lab to a mock-up nuclear power plant, where we investigated if they can be used for radiation measurements. We also fly outdoors in challenging conditions, such as at winds up to 28 kilometers per hour. And here we test if we can fly vision-based, if in the case of GPS failure. We work on off-road vehicles, as well as on-road vehicles. So here we participated 4 years in a row in a self-driving competition organized by General Motors, which we won each year. And each year they, the scenarios got closer to self-driving, real self-driving applications. And the last thing you saw was our mobile manipulation platform. So these are the robots we work with every day, and they move in our lab every day. And we want our main goal is to achieve high performance control of these mobile robots in increasingly complex situations. And that's where machine learning became a really important tool from the beginning. And it really started with my PhD, where the simple goal was, we want to show the agility of flying vehicles. And to do that, what better example than doing slalom trajectories as fast as possible. And so we did that. I had a pretty good simulator and designed a controller. And when I went to the real world, this is what happened. And that motivated right away learning in the real world, because our simulator was pretty good. But the effects that happened here are very complicated aerodynamic effects that are sometimes not even qualitatively well understood, nor can you find the quantitative model and the parameters of that model very easily. And so what we did at the time is we learned in the real world, because there was no simulation that would capture the behavior that was causing these issues. And so we learned in the real world above the poles. And we didn't start learning from scratch. We used our prior knowledge. And therefore, we could learn quite quickly corrections to the nominal input trajectory, such that we could actually fly around the poles. And that after 3 iterations of training. And so here you see the the configuration where the vehicle failed before, and you see it flies at quite high pitch angles, which causes, you know, these complex aerodynamic effects. And so that was like the beginning of where I saw, you know, data can be used to improve performance. And the setup was like this. So we had our system with a baseline controller, which failed in this task of slalom trajectory, but the baseline controller would still stabilize the system. So we have a standard control loop for people familiar with, you know, control theory, and the controller is based on the model. And the advantage of this low-level control loop is that it compensates for noise and disturbances. But then at the high level, it couldn't track the output trajectory that we wanted. So what that means is we input as a reference signal the desired trajectory in blue, but what we really saw as a result was these colored lines. So we saw repetitive errors. And, you know, the good thing, it's repetitive. And the reason is that this underlying controller compensated for a lot of the noise and disturbances that would affect the robot's behavior, and you know, made the robot behave in a systematic way, which is already a big step forward. And then we could use a relatively simple adaptation of the reference signal, the screen box, to cause those colored lines to be closer to the desired blue line. So to cause the actual output to be closer to our desired output. And what we saw, if we kind of did this iterative update of the reference trajectory, and it's basically a gradient-based approach where the gradient is given by our prior model, so that makes it so fast to learn. But what you see is, you know, iteration 1 here in this plot here at the bottom left is the nominal input trajectory, the reference trajectory. And what the learning does is it commands a reference that, you know, commands amplitudes that are larger and earlier, such that the robot has time to react. So that was the first kind of venture into machine learning for me. And it was directly learning in the real world on a quite challenging system, a flying vehicle that could, you know, easily fall out of the sky. But this architecture helped to stabilize the system and use machine learning only to improve performance, right? And then we tried to, oh yeah, and here you see the result for the specific example. So we then extended this architecture, because what this architecture meant is that we need to learn a single task through repetition. So each new slalom configuration we had to learn from scratch. And so we changed this architecture in a way that we learn an inverse model, and we use a deep neural network, but probably other nonlinear regression methods would equally work. It's basically this green box should be the inverse of the gray box, with the result that we have a unit mapping from the desired output to the actual output. And so in this case, we still learn offline, right? But from real data, we collect a bunch of real data on the real vehicle and then learn this inverse model. And so here you see an example in the lab. So different people draw different trajectories. And with one learned inverse model, we can follow those trajectories quite well, which you see in green, and the light gray always represents what a nominal non-learned controller would do. So we usually have an error reduction by 60% or something like that. We can also use, oh, sorry, this was dumb. We can also use this to catch balls. And here, you know, the ball is thrown from arbitrary directions, and it's important that the learned model can capture those and compensate. And so here you see the learned result. When we throw the ball from different locations. And the inverse model helps the mobile manipulator to be very precise in time and space to catch the balls. And this is all real time, right? It has to be very, very precise to catch the ball. And it's a very narrow opening. And so we are not perfect. We have maybe, with the learning, we have roughly a success rate of 85%. And here you see some failures. So here we didn't predict the ball very well, which is something you could also learn. And here our tracking was still not good enough. So these two architectures learned from real data and had this underlying feedback controller to make the system still safe. And safety in this context meant that we can actually formally in these papers guarantee stability. So a flying vehicle doesn't fall out of the sky, or the mobile manipulator doesn't, do crazy motions. But safety can mean something else as well. So we saw stability, but it can also mean constraint satisfaction. So in this, this is just an example from a very recent work of us. But here you see, constraint satisfaction means moving around the pole and balancing these objects on the tray and have them not fall. So those are two constraints. And so ultimately, the question with safe learning control is, how can we use data to improve a robot's decision-making under uncertainties? I mean, there's things we don't know ahead of time that motivates learning in the first place, but also adhering to given safety constraints. And I think that's particularly important if you learn and adapt in the real world from real data, right? And so my group has worked on the safety aspects of learning for a while. And so one thing I want to do in this talk is I want to give you a quick update on the state of the art, because we did a review paper in this direction. And give you some examples from our research, but then also present some open challenges in this field and how we hope to enable progress in the future. So let's start with this. So the safe learning in robotics field is driven by really two separate communities, the controls and the reinforcement learning communities. And there was little mutual understanding and a lot and connection between the two fields. So our goal was with a review paper or survey paper to bring these two fields closer together and review, what have people done to date to guarantee safe learning of robots in the real world. And so I encourage you to look at the review paper. But what we found is that really all the problems that have been posed in the safe learning field can be represented as an optimization problem, where you minimize the cost, or inversely in reinforcement you usually maximize the reward, but that's the same, right? So you want to minimize a cost subject to possibly unknown dynamics of the robot and subject to safety constraints given an initial condition of the robot and a policy, and you optimize, the optimization variable is to find that policy pi. And so what is different to typical, maybe standard reinforcement learning approaches is that you have these safety constraints. And so then we define the safe learning control problem as mapping of any prior knowledge about possibly the dynamics or the costs or the constraints and data to the optimal policy. And I think that's something interesting to consider, that if you want to guarantee safety, often you need some prior knowledge to get started, at least to start very conservatively. And then we generically call this data. Data could be from pre-training in simulation, which could give you, a first first set of policies that and possibly safe policies that you then want to test in the real world. So data could come from simulation and from the real world, and and in addition, often you have some form of prior knowledge, and you want to basically take everything that you have to find the best policy. And so in the literature right now, safety guarantees can be categorized into 3 levels. Soft constraints means we try to encourage the robot to not violate the constraints, for example, through a cost function component. Probabilistic constraints means that the algorithm guarantees no violations with high probability. And then there are hard constraints, which means that the learning algorithm guarantees no violations. And so in the literature, you can kind of try to categorize the approaches for robot learning with safety considerations in this diagram, where on the y-axis you have, the safety levels from no guarantees all the way to hard constraint satisfaction. And on the x-axis, you have the amount of prior knowledge you assume you have. Fully known dynamics on the left, and then completely unknown dynamics that could be any hybrid, non-linear component. So and often approaches are in the middle, which means they assume a certain structuredness of the model. And so standard control approaches lie here on the left, where, if you know everything, you don't need to learn, and you can usually provide hard constraint satisfaction. And so that means you know the model perfectly, or you may know it with bounded uncertainties, but the bounds of the uncertainties are known and correct. So you don't need learning. Then vanilla reinforcement learning is here at the bottom. It makes no assumptions, but also usually no guarantees on safety, right? And so a great example is this from OpenAI. I mean, very impressive and very complex dynamics. Very hard to capture those dynamics in a simulation, even so they did. But what you don't see is that for the maximally difficult scrambles, the RL result was only successful 20% of the time. And so 1 out of 5 times it was successful and could solve the Rubik's cubes, and 4 times the cube fell or it gets stuck or timeout. And so you see there's no guarantees that this will work, right? It's very impressive, but no guarantees. And so then people have worked on filling this wide space, and one direction is safely learning uncertain dynamics. And that is something that my group has been working on for some time. And so here you see, basically you assume, have some nominal dynamics and an uncertain component, and this uncertain component you may represent as a Gaussian process, where initially you know nothing, so the function could be anywhere in this blue shaded area. And as you get better knowledge about the underlying dynamics, this blue envelope shrinks. So as you collect data from the real robot, the blue envelope shrinks. But the blue envelope always represents a conservative envelope of where the function lies. And then you can combine this with robust control methods and guarantee real time in the real world learning with each data point. And so here you see just a simple example. If we drive a robot off-road and with the wrong model, we hit those pylons and we don't stay within the path bounds. But then if we start learning with such an uncertainty based approach, the robot drives initially very slowly to keep the uncertainty envelope in purple within the path bounds over, say, the next 5 seconds. But from the data it collects, it gets a better understanding of its own dynamics, reduces the uncertainty. And here you see the third trial that the uncertainty is, is much smaller, and it can try faster because even at a higher speed, it can keep this purple uncertainty envelope within the path bounds. And so some similar approach with Gaussian process can also be used for automatically tuning a controller, where you only test controller gains that are safe with high probability. So you slowly expand kind of the area, and you model the underlying performance function as a Gaussian process, and eventually you find the optimal gains, and you can automatically and safely tune a controller. So these are probabilistic methods, and they work with every single data point that we collect. We can update the model in real time and get better. So we can basically update the Gaussian process at 50 Hertz. Another interesting approach in the literature, more recent, is to make any learning-based controller, which could be an RL agent, safe by transforming the uncertified input into a certified input through a safety filter. So basically, there's some additional component that guarantees that the input does not destabilize the robots. So the idea is that it could be added to any RL agent, maybe possibly even initially trained in simulation and then continue to be updated with real-world data. And so one approach from our work is this one, where we use a Lipschitz network as an adaptive approach. So it is a neural network trained, updated in real time with real data. It's a small network. But if we assume that the underlying robot system is L2 stable, then we can provide a guarantee that this system is safe. And for that, the Lipschitz constant of the neural networks needs to be smaller than this L2 gain of the underlying system. So this L2 gain you can approximate easily from a simple experiment, or you can also guess a conservative value. And then basically you update the weights of a neural network in real time, at 100 Hertz. But you use a network structure that guarantees you that the network has a bounded Lipschitz constant. And so you basically adjust the input each time in a way that the Lipschitz constant of the neural network is bounded, and therefore this whole closed loop system is bounded. And so we have used that. Yeah, so the Lipschitz network then has a prescribed Lipschitz constant. And so we have used this to balance a pendulum on a standard commercial drone platform, which is very challenging. So we used a model of the robot and the pendulum and try to stabilize this, but it's very difficult. So now the underlying Lipschitz adaptation makes the robot behave like a reference model, and then we can actually achieve balancing. More details, if you read the paper, I can also answer questions about this later. So the white area is not fully filled. So there's also reinforcement learning algorithms that encourage safety and robustness by adding, for example, a component to the cost function, but they usually just encourage safety, right? And really the ultimate goal is to go to the top right, to have guarantees as much as we can have as we learn in the real world, and do that for very complex systems with contact and interaction, possibly with humans. but there are many open challenges right now. And I just want to emphasize a few quickly. So yeah, the safe learning field is really at the beginning, in my opinion. So right now, all the results, and you can see that in our review paper, are for ordinary differential equations. So assuming that the true dynamics, even so they are unknown, are ordinary differential equations, and then the safety guarantees hold. But what about hybrid dynamics, such as grasping something, or complex soft dynamics, like soft robots, like on the right? Also, scalability of these approaches sometimes still a challenge, often, especially on the more safe reinforcement learning approaches, take many hours to train for a simple inverted pendulum you see on the left. But ultimately, we want to put this on possibly flexible arms in space. Right? And then all approaches right now assume they have possibly noisy measurements, but unbiased measurements of the state of the system. But really, I mean, in practice, we have high dimensional sensors and multiple sensors like cameras, IMUs, and etc. And then we still have to first estimate the state. And then to guarantee anything, you need to make some minor assumptions. And sometimes that just means that the disturbances are bounded, or that the unknown dynamics have a certain condition, certain continuity assumptions, such as Lipschitz continuous. But how do we verify these assumptions in the real world? And what do we do if they don't hold? And finally, I think it's also really interesting. Right now, we tell the robot what is safe, meaning where the walls are, where the obstacles are. But in the future, it could figure that out itself, right, from a semantic understanding of the world. So understand the world, and then from that derive these safe controllers. And so since there's still a big gap, and from our review, which included over 80 papers, we have seen that the evaluation goes from, very simple examples such as grid worlds to simulations in the OpenAI gym environments to real robots. But overall, of all the all the papers, less than 30% had hardware experiments, and less than 20% had open source code. So we thought there's really a gap towards bringing these algorithms to the real world. And so as a result, we developed Safe Control Gym, which is a benchmark suite. And the idea is that it enables you to test safe learning-based robot control. It's a physics-based simulation as a compromise between realism and accessibility. So ideally, we want you to learn in the real world, right? But I mean, for that, we would all need to have the same or comparable hardware. So we opted for a realistic simulation, but the simulation has an option to do sim to real transfer from a quadrotor simulation to the real world. And so what are the key features? The key features are things that we haven't found in other environments. So we can include prior knowledge. There is a way to specifically define safety constraints, and we can introduce disturbances in various levels to make it as close to the real world as possible, and it's compatible with all the gym environments. And right now it has a card ball and a quadrotor as examples, and the two tasks of stabilization and tracking, but people are expanding both on the robot system side as well as on the task side. But this really enables benchmarking of different learning approaches. You can also do like offline training, and then kind of so mimic offline training and then online training. or do full online learning, as most of our approaches from my lab do. And so the really good thing about using this environment is that many standard approaches are implemented for you already, which makes your comparisons in your paper is much easier. So there's standard control in RL approaches, but also the latest safe learning approaches implemented. And so this environment just allows you to compare various learning approaches, kind of real time in the real world learning approaches as well, with a specific focus on safety. But even if safety is not what you are interested in, you can use that. And for some results that we got already, just as an example, is you can now compare a model-based learning approach where it has a prior model, but the prior model is not a perfect model of the real world, right? So it has, in this case, actually we overestimated the model parameters by 150%, so quite wrong. But still, you see with the wrong model, this model is still a good starting point, and you can save 2 magnitudes of data while still getting roughly the same performance. So it just allows you to do lots of comparisons, etc. And then we also took this to IROS, and there was a safe robot learning competition there, where people designed controllers to fly through gates. And here you just see the winning teams work, where they fly in the simulation through the gates and learn this task under disturbances. So they do real world learning. And then we actually, and that's the sim to real component, we can actually fly this now in our lab in Toronto. And so it's actually in the real world. And so, yeah, as a summary, I hope I could convince you that safety is important in real world learning. And hope you can check out the Safe Control Gym benchmark. And there's also a Safe Robot Learning webpage that includes also previous workshops in this direction. And you can sign up to a mailing list to learn whenever we organize something in the future, like a competition or or a workshop. So thanks so much. Finally, if you are interested to continue working in this direction of learning for real robots with guaranteed safety. Currently, my team is both in Toronto and in Munich. We've rebranded as Learning Systems and Robotics Lab, and if you're interested, we are hiring. And all the recent updates are found under the tag LearnSys Lab. Thank you.
Thank you so much, Angela. So yeah, we'll be taking audience questions or any like virtual questions. Yeah. So I have a couple of questions. So I really liked your work on incorporating safety filters to any learned agent, and I was wondering if this sort of Lipschitz constraint idea could actually be or how would we modify this setup to be able to handle like visual inputs or like things that are getting like depth or RGBD information.
Yeah, I think for the safety filter, the good thing is that the learner can be quite complex and take all this high dimensional data, and for example, use deep RL to learn it, possibly in simulation. But then the safety filter modifies the output if needed to make it safe, right? If the simulation was good and accurate enough, then the safety filter actually doesn't do anything. There is a caveat though, that the safety filter makes an assumption about the model or the dynamics of the system, not of the deep RL, but the underlying, the real robot. And so that may be okay for a mobile robot and even a mobile manipulator. You can make these assumptions and you can kind of find a conservative model with conservative disturbance bounds. But it's harder for things that, where you have contact. But yeah, it basically the safety filter itself in the broad, like the standard approaches, the safety filter needs to make some model assumption, even if it's conservative. Yeah.
And then another question, like inspired from your response, is let's say we had a contact heavy task, or like maybe a more difficult task to model than something with something beyond ODEs. Could we, for example, use what are the assumptions that would be made for something like catching or throwing, something more like a more dynamic manipulation task?
Yeah, I think first, I think there's a lot you can do by still defining what safety means in that context, like mathematically. I think this is, you could do a PhD about that. But I think overall, the approach should be, we should be able to extend it, because I mean, contact, yeah, you can model it still as even as a continuous differential equation where the contact, is not abrupt, but instead of you not touching and suddenly touching, usually if you have, it depends what your gripper is like, but usually it's actually a smooth function, right? And so if that is true in your case, maybe you actually design your gripper in that way for various reasons. But for one reason being that maybe you can better apply these kind of safe approaches to it. Yeah, I think it's harder if things happen suddenly, but many of these grippers are soft, and actually the kind of contact function is not a sudden jump, but something continuous.
Cool. Very cool. Yeah, we're running again a little bit late, but thank you so much for taking the time. Really appreciate it. Great, really cool results and work that you and your lab have been doing. And yeah, again, thank you so much for your talk.
Thank you. Thanks everyone.
Yeah, hopefully we'll. So you're coming to New Zealand, right? I think you're muted, but yeah, thanks again. Yeah, we'll probably end the session here right now, and then we'll resume at 2:30 after lunch and the opening session. Thank you so much. Thank you, Angela.
Thank you. Thanks everyone.
Okay, so let's get started. So our next speaker is Chelsea Finn. Chelsea is an assistant professor in computer science and electrical engineering at Stanford University. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. So to this end, her work has included deep learning algorithms for learning and visual perception and control in robotic manipulation, as well as meta-learning algorithms that can enable fast few-shot adaptation. Her research has been recognized through the Microsoft Research Faculty Fellowship, the ONR Young Investigator Award, and the ACM Doctoral Dissertation Award. So with that, Chelsea, take it away.
Thanks, Annie. Since we have a small crowd, feel free to interrupt if you have any questions about, any clarifying questions or any questions about what I'm presenting. So I'm interested in how we might allow robots to develop broadly intelligent behavior. And my lab has looked at this problem from a variety of different angles, such as some of the works that are shown on this slide. And my work in robot learning actually started back in 2014 with reinforcement learning. And we're really interested in how robots might learn how to train neural network policies end to end through trial and error. And from there, a lot of our work has stemmed out to expand to other directions, but also still kind of keeping a lot to the root of reinforcement learning. And I think that reinforcement learning is still something that is going to be a really critical component of robotics, because it allows robots to learn from their own experience rather than from data that's collected in other ways. But I think that at the same time, while reinforcement learning, I think, is really critical for the future of robotics, it also is rather challenging to use in practice. And behind the scenes, if you actually have run reinforcement learning on a real robot, it often looks something like this, where the robot attempts the task and then needs to kind of attempt the task again. And so a person will come in, sometimes it's me, in this case, it's my friend Yevgen, and they help out the robot by resetting the scene and allowing the robot to retry the task. And one thing you might notice here is that Yevgen is actually doing more work than the robot is doing. And it's really not going to be practical nor scalable to use this kind of approach in the real world. And so despite all the promise of reinforcement learning to allow robots to learn from their own experience, I think that we need to address some of these really critical shortcomings in order to allow robots to learn and adapt in the real world. And so towards allowing robots to learn in the real world, not just in lab environments, I think that a really key roadblock is autonomy, is their ability to learn from their own experience without a human constantly intervening and supervising the process. And so what I'd like to talk about today is primarily talking about kind of imbuing robots with autonomy during the reinforcement learning process. And if we have some time, I'll also talk a little bit about autonomous adaptation at test time as well. Great. So we saw that kind of Yevgen was resetting the robot there. Let's actually kind of dig into that a little bit more. So in reinforcement learning, we typically collect trajectories that are sequences of state actions and sometimes rewards. And the trajectories can be written like this. And typically we kind of break up our trajectories into these episodes, and each episode ends at the final state, SH. And somehow we need to get from SH to the beginning of the next episode. Now, in simulation, oftentimes we call kind of environment.reset, and that will get us back to that initial starting state. But in the real world, we can't just ask the real world to go back to a certain state. And as a result, when we actually deploy these algorithms, we deploy people like Yevgen or myself or whatever graduate student or undergrad you would like to help run the experiment. And this ultimately is preventing the autonomy of the robot. And so it's not just about having undergrads do less work, it's also about actually giving a really fundamental capability to robots in the reinforcement learning process. Now, you might wonder, well, instead of calling end.reset, what if we just run reinforcement learning algorithms, existing reinforcement learning algorithms, without those resets? What if we just continue the episode onward? And so we can actually do that. So we did that. There's a really simple DM control environment, like really very simple environment. And if you give the agent a reset every 1,000 time steps, you'll get a pretty nice learning curve that looks like this. If you give it a reset every 2,000 episodes, or sorry, every 2,000 steps, it starts to do a little bit worse. If you give it a reset every 10,000 steps, or every 50,000 steps, or every 100,000 steps, the performance continues to degrade to the extent that it's not actually now learning a policy that can successfully solve the task. This is just a really simple environment. And this problem gets exacerbated as we move towards more complex real-world robot environments. And I should emphasize here that the y-axis here is measuring the evaluation performance of the policy that it's learning, not the return during training. This is how good is the policy that we're learning with these fewer resets in the environment. And this was actually a result that was surprising to me. The first time I learned about this problem, I kind of assumed like it seems like this problem shouldn't be that hard. And it turns out that's actually quite difficult to allow robots to learn autonomously. So why is it difficult? So typically in episodic learning, maybe you want to kind of start from some initial state distribution and learn a policy that goes towards some goal distribution. In episodic learning, you can collect trajectories starting from your initial state distribution. You can always retry the task from your initial state distribution. And in contrast, in kind of a more autonomous setting, when you don't have these episodes, first you collect an episode, or first you collect some experience, and then you need to start from here rather than starting from the initial state. So then you collect some more experience. And one of the challenges that arises is that your exploration can cause the agent to drift quite far away from the states that are actually along the kind of the optimal state distribution, the state distribution of the optimal policy. And if it wants to kind of go about and actually like learn a good policy, it needs to actually find its way back on itself, on its own, rather than relying on a reset to get it back there. And so it actually ends up having to cope with the fact that it's seeing a much larger part of the overall state space. So that's one challenge. Now, if it does actually eventually kind of make its way to the goal, another challenge is that it may actually just stay near the goal because it's accumulating reward there. And the state distribution that the data that it collects may actually only be around the goal rather than around this distribution right here. And that means that if you're only collecting data near the goal, you won't actually learn a good policy that goes from the initial state to the final state distribution. So these two main challenges that make autonomous reinforcement learning difficult. Now, one existing approach for trying to tackle this problem is to learn two policies, a forward policy and a backward policy, where the forward policy tries to learn how to solve the task and the backward policy tries to learn how to reverse the task. And this approach can address the second challenge because it will actually explicitly try to kind of go back toward the initial state and give you a good state distribution that kind of resembles the states that you're going to be seeing, or resembles the states that are kind of nearby the expert state distribution. That said, it doesn't necessarily address the first challenge. The agent could still drift away, and it may still be challenging to kind of get back towards that expert state distribution if, for example, you have sparse rewards for getting for the forward task and for the backward task. So what we wanted to do is we wanted to try to address both of these challenges, and we are going to, one thing that we're going to do is we're going to assume that we have a set of demonstrations available. This set of demonstrations can be provided at the very beginning of training. And then after those initial demonstrations are provided, we can then have this fully autonomous learning period. And so requiring these demonstrations isn't going to, because we're kind of only needed up front, the supervision up front, we're still going to have an approach that's quite scalable in terms of being able to collect and kind of autonomously operate in the world. And then what we're going to do is we're also going to learn a forward policy and a backward policy, but rather than having the backward policy try to get to the initial state distribution, we're going to try to have the backward policy kind of go towards the distribution of the optimal of the expert. And so the forward policy will act, the backward policy will try to kind of then stay close to the expert state distribution, specifically the states visited in the demonstrations. Then the forward policy will act again and try to attempt the task, and so on and so forth. And this algorithm is very simple. It just still has, again, these two policies, one that is going forward and one that tries to match the demonstrations. But it has a number of appealing properties. So first, by trying to visit the states visited in the demonstrations, this is going to help shape the reward function and help the agent avoid drifting away from that state distribution. So that's addressing challenge one. And second, the backward policy is going to, like in forward backward RL, we're also going to avoid the collapse of the distribution from the goal distribution because the backward policy is going to be specifically trying to visit all the states in the demonstrations, which will be a much wider distribution than just the goal state. So these are kind of addressing these two challenges. And then there's also kind of a bonus property of this, which is that it means that the forward policy is going to be attempting the task from all the states that the backward policy reaches. And the backward policy is going to be trying to reach states all along this trajectory. And this means that the forward policy will be attempting the task both from easier initial states as well as harder initial states. And this is going to implicitly create a form of curricula for the forward policy to learn from. And there's actually a nice theoretical result from 10 years ago that showed that this sort of initial state distribution is actually beneficial for learning compared to learning a policy only from the initial state distribution. Cool. So to kind of recap the algorithm, we have a forward policy, a backward policy. The forward policy is just maximizing expected reward. This is a standard reinforcement learning objective. And then the backward policy is going to be trying to match the expert state distribution, which we will approximate with adversarial imitation learning on the states visited by the expert in the demonstrations. We're doing this on the states only, whereas things like Gale typically do states and actions. And then when we actually go about collecting data, we're going to be alternating between running the forward policy and running the backward policy. Cool. And so we experimented with this approach on a few different environments. I'll highlight a couple of the environments here. These environments were taken from a benchmark from previous work. And during training, we actually are going to give it resets periodically, but we're only going to give it resets every 200,000 steps. Typically, environments give resets every 1,000 steps. So this is 200 times less human involvement. And then for evaluation, we're going to be evaluating how well the policy performs from the initial state distribution. We're going to be comparing to a number of different prior works, including forward, backward RL. And let's first look at this task of closing a door in simulation. This is what the kind of the policy performance looks like as a function of the number of training, of the number of environment steps. This is a lot of curves, so let's kind of break it down one by one. So first, the gray curve, the gray dashed curve, corresponds to an oracle that gets resets every 1,000 or so time steps. So if you get resets, you can learn the task really easily, but if you don't, it becomes a lot more challenging. And if you don't give it any resets and you just run vanilla SAC or soft actor critic, you get the blue line, which as we can see, doesn't actually learn a good policy. Next, if we introduce a kind of a state novelty exploration term, which was proposed in a prior method, we do a fair bit better than vanilla SAC, but we don't learn a policy that is has a high success rate. There's also a prior work that introduces a goal curriculum, and also forward backward RL actually does fairly well in this case. But the approach that I mentioned before, where we're actually trying to match these expert distributions or metal, is doing much, much better, both in terms of the final policy performance and also in terms of the efficiency. And the kind of efficiency is what we might expect from like kind of really truly leveraging the demonstrations. And I guess I should mention that all these prior methods are also using the demonstrations by seeding the replay buffer. And so we do have a head-to-head comparison here. Great. And then we looked at a number of different environments. For one more environment that I'll show, this is a peg insertion task. This task actually ended up being a lot more tricky because the peg can kind of eventually get into places that are very challenging to pick up. And in this environment, we found that kind of all of the prior methods really struggled to learn this task. And only metal was able to actually start to get a policy that can succeed some of the time. Great. And then all of the results that I showed so far were kind of presented in an ICML paper early this year. And we've also been recently experimenting with this method on the real robot. Unlike the other experiments, the real robot experiments are from pixel observations. And we don't have the ground truth reward function. And so we're actually learning a reward function for the forward task as well. And the goal was to try to basically be able to pick up a towel and kind of hang it into this loop on this hook right here. And we seeded the training with 50 demonstrations, and behavior cloning was able to get a success rate of around 26%. There are some like initial positions of the towel in which the behavior cloning policy struggled. And in contrast, if we run kind of an improved version of the algorithm that I presented on the previous slides, we see that kind of over the course of training, this is kind of a time lapse of the training process. It's able to learn a policy that can that does start to succeed some of the time. And the here's like the whole training process here is kind of over the course of a few hours, but this is a kind of a 30-second sped up time lapse. And the final success rate of this policy after running this autonomous learning period was 62% success, so much better than the behavior clone policy. And then you might wonder, okay, what is kind of getting us from metal to metal plus plus? There's a number of things that were actually really important for allowing the robot to learn in the real world. This included learning rewards, like I mentioned. We learned rewards using the Weiss method. We found that we needed to apply heavy regularization to the learned reward function to avoid RL from exploiting the reward function. We also found it helpful to regularize the policy to the demonstrations with a behavior cloning loss, to oversample the demonstration, the transitions in the demonstrations when training the Q function. We also used a wrist camera, which you can see right here, in addition to a third-person camera, and we found that to be pretty helpful. And then we also changed the underlying RL algorithm from SAC to REDQ, which can significantly help with sample efficiency. This is somewhat anecdotal for now, but yeah, it's kind of preliminary results and something that we're kind of writing up and working on, kind of fully fleshing out in the coming months. Cool. So the intermediate takeaways here is that first, autonomy, I think, is a really important ingredient for robots in the real world. Reinforcement learning algorithms work surprisingly poorly if you don't give them resets between episodes. And METAL is a simple and practical approach for enabling autonomous reinforcement learning. That said, there's still lots of work to do, lots of challenges. And kind of what I'd like to talk about next, and kind of one of those challenges that still exists, is you might have noticed in this video, there's kind of these guardrails around the environment. And a lot of reinforcement learning settings, we construct environments that kind of are somewhat closed off so that things can't kind of be pushed away and so forth. But if we actually want to put reinforcement learning into the real world, we're not going to have guardrails around the robot environment all the time. Cool. So I'd like to start talking about how can we actually handle scenarios where there aren't that kind of guardrail. And we can consider this more generally as environments that have irreversible states. And so we'd like to essentially, if there are states that a robot enters that are irreversible, such as pushing an object off the table and it can't reach that object, we'd like the robot to be able to proactively ask a human for assistance in those scenarios. And the reason why we want to do that is, well, first, it's kind of impossible for the robot to recover from that state. And second, if you could, like, the alternative is basically to have a human constantly watching the robot, checking if an object has fallen off the table, or checking if it's entered some other irreversible state. And if you require that constant oversight throughout the learning process, then you've kind of defeated the purpose of autonomy. And so we'd like to build a framework that allows agents to both detect these irreversible states and try to avoid them. But if it does actually end up in them and it detects that it's ended up in an irreversible state, it should proactively request an intervention and send you a text message or send you an email or whatever if it's entered that state, so that it can get help. Cool. So formally, irreversible states are states that kind of belong to a different strongly connected component than the initial state. So you can think of all the green states here as states that are reversible. You can get back to kind of the start state from those states, and all of the red states are states that you can't return back to that start state. And so this is how we define irreversibility. And we're also going to kind of within this problem setting, allow the robot to request resets and to query for reversibility labels, basically to ask a person if a state is irreversible or not. And in principle, you could allow the robot to try to fully kind of autonomously figure out which states are reversible or not. But in practice, oftentimes a person can pretty easily look at a scene and tell the robot if it's irreversible or not. And we find that allowing the robot to query for a few labels will substantially increase the efficiency of the learning process. Cool. Now, this problem of avoiding irreversible states is closely related to the problem of safe reinforcement learning. And safe reinforcement learning tries to avoid unsafe states. Irreversible states are not necessarily unsafe. It's okay to drop an object off the table if it's not fragile, but we still want to avoid them. And so we can similarly borrow from the SafeRL literature and designate irreversible states as undesirable, as basically using a reward penalty for those states, and then kind of train with reinforcement learning. But one thing that CoRL doesn't give us is that it assumes that these methods implicitly assume that every visited state, you know whether it's a safe state or an unsafe state. And in practice, the robot won't know if it's entered a state that is irreversible or not. And so again, if we require labels for every single state, this would again kind of preclude autonomy. It would require human oversight, and we'd like the robot to be able to be much more label efficient in terms of learning about irreversibility. Cool. So how do we do this? First, we're going to just train a simple binary classifier to estimate the reversibility of a state, basically to take as input a state and output whether or not it's reversible or irreversible. Then, well, first we can use this binary classifier to kind of predict the reversibility of new states. But when actually training this binary classifier, we can actually train it very efficiently using much fewer labels than labeling everything. We can do this with a very simple observation, which is that if we know that a state is reversible, then we know that all the states before that are also reversible, but kind of by the definition of reversible. And likewise, if we know a state is irreversible, then we also know that everything that comes after that is also irreversible. And with this observation, you can basically run kind of a binary search to find where did you enter the irreversible part of the state space. And that means that you could use, for a given kind of long trajectory, you only need a logarithmic number of labels rather than requiring labels for the entire trajectory. Cool. And so what we're going to do is we'll train this binary classifier with these labels, this logarithmic number of labels, or logarithmic number of queries, and then we can use that to label the entire trajectory. And then in order to get a little bit more data of irreversible states, we're also going to explore the environment after we've entered an irreversible state to collect more examples of irreversible states. And we found this to be helpful because if as soon as you get to an irreversible state, you stop and don't get any more data, then you just aren't going to have that much data or that much information about what states look irreversible versus not. Cool. So to summarize, we have a robot, we have a buffer, kind of this typical off-policy reinforcement learning setting. The robot can request an intervention, and this will kind of reset the environment and allow it to continue practicing. And when it requests an intervention, we're also going to label the trajectory that it collected from the previous intervention to the current intervention using a logarithmic number of labels. This will be added to the data buffer. We'll use this to train the classifier and kind of improve our estimation of whether we need an intervention or not. Then the robot is reset to some initial state from the initial state distribution, and this process repeats. We refer to this framework as proactive agent interventions, or PAINT. And we evaluated on a number of different scenarios that have irreversible states. So this included scenarios in which a mug was out of reach, scenarios in which we took the peg insertion task and removed the guardrails. And we actually also made the table smaller to make it even harder. And then we also evaluated on this kind of simple half cheetah locomotion problem where the agent can flip over on its back. Cool. And so in the results we looked at, well, I guess first, typically when you plot reinforcement learning curves, it's like number of data points versus performance. Here we're actually gonna be looking at the number of human interventions versus performance. And this is, I think, actually a better measure of kind of the amount of effort that, at least human effort, that goes into the process. And what we see is paint is shown in blue. And then there are a number of prior methods, including a self-supervised reversibility approach, kind of standard SAC, as well as, and actually this SAC is kind of using a reset every 2,000 episodes or 2,000 time steps. And then also this prior approach called leave no trace that is related to forward backward RL. And we see that in general, paint is able to learn a quite good policy with far fewer human interventions than prior approaches. And so in many cases, it requires 15x fewer resets, and it only requires around 80 to 124 resets for learning. And then for the half cheetah environment, it's actually the only method that gets anywhere close to Oracle performance. And lastly, we can also compare to safe reinforcement learning methods that require labels for every single timestamp or time step. And what we see is that it requires on the order of 100x fewer labels than these prior safe RL methods, which isn't too surprising because it's using this kind of logarithmic trick to label the examples. Cool. So the takeaways on this part is that robots should detect and avoid irreversible states to learn more autonomously, and providing these sorts of reversibility labels, this is more costly in terms of supervision, but it can really substantially improve the recognition of irreversible states with a fairly small number of labels. Cool. I think that we're pretty low on time, so I think I'm going to end there and skip the last part of the talk. I'll share my screen again in a second. And so the kind of overall takeaways is that I think if we give robots autonomy and initiative, it can make reinforcement learning in the real world more practical. There's simple techniques like reversibility classification and staying close to demonstration data that can really improve the autonomy of reinforcement learning systems. I didn't get to talk about it, but autonomous learning at test time can also allow robots to handle novel situations. And lastly, there's also still tons of work to do on this front for making reinforcement learning practical on real robots. And yeah, really excited to see where that goes. I'd like to thank the students in the lab and happy to take some questions. Thanks.
So next one, do you think there's any value in extending the intervention with the robot actually asking a reset to a particular state that has been unexplored or underexplored?
Yeah, so in this work, we only ask for like a binary, like, do you want an intervention or not? And it just resets to the initial state. I definitely think that if you ask for like a more specific kind of intervention, that could make learning even better. And in some ways, you could think of the first work as suggesting that maybe actually it's good for it to reset not just to initial states, but it kind of states along the kind of expert trajectory. And we also actually have some work kind of on goal curricula and so forth that we've done in this space as well. It does make the algorithm more complex, and you need a way to specify what that state is. And if you're operating from like image observations, for example, that might involve like generating an image of what you want it to look like, which just increases the complexity a lot. But certainly I think that that'd be interesting to explore. It could also be cool to request for interventions in natural language as well. And that would maybe not give you a full specification of the exact state, but say, can you pick it up off the table, or can you kind of put it in my hand or something like that? Yeah.
Is that chosen by you guys prior to like match to? Like, is it how order established? Select guys.
Yeah, so the row star is implicitly defined by the demonstrations. And so it's just, we're training a discriminator to discriminate between the states visited by the policy and the states in the demonstrations. And so it's not really manually defined, it's just kind of implicitly defined from the demonstrations. Yeah.
Because if you have a high and you have a very discriminator on the other side, will the reinforcement just collapse, not doing anything because it's powerful?
Yeah, so for the first question, in terms of the when to reset between, like when to change between the forward and backward, we found that the algorithm wasn't too sensitive to that choice. We just picked a fixed hyperparameter, like a certain number of time steps to decide. Like if it's been like 2000 time steps or something, it shouldn't be too small. It shouldn't be like 1 or 2, but generally like we found that if it's something that's like along the lines of a typical episode horizon, that worked just fine. The second question, what was the second question again? The density of the expert demonstration. I don't think it needs to be particularly dense. Of course, if you have a lot of demonstrations, it's possible that behavior cloning just already does really well. And if you're in that case, you should just train a policy with behavior cloning. Although one thing I will say, I didn't get a chance to talk about this, but in some of our real robot experiments, we did find that even in cases where behavior cloning does quite well, the policy learned with reinforcement learning is more robust to wider initial state distributions because it ends up visiting more initial states than what is seen in the demonstrations. But yeah, I don't think it needs to be too dense. And if it is very dense, then I don't think it'll be harmful if it's very dense. Well, it may be harmful actually if it's too little dense, but we also, like I mentioned in the real robot experiments, regularization on the discriminator was quite helpful.
I think we'll move on to the panel now because Chelsea will also be here. So if you have the audience has more questions, we can ask them in the panel. You can ask the panelists to come down and get seated. And Ben, you managed to pin put the I don't know. That's I'm gonna make this full stop. Yeah, so unfortunately, there's only one mic. So if I could ask you guys to move your just a little bit closer, and then just so that you guys are the audience's view is not interrupted. Yeah, so that the panelists are not obstructed by the audience. So yeah, so the way this will work is that we'll basically have the moderator, so the organizers will ask a few questions, and we have some of our speakers and some guest panelists from the spotlight papers, and we'll basically first ask a couple of open-ended questions, and then we'll explore certain important themes for this workshop, like the role of the physical worlds / benchmarking, pre-training versus fine-tuning, using passive data or simulation or none, and exploration. So we'll have these themes, and we'll start off the question, and then we'll open it up to the audience for each of these themes. So without further ado, let me get Unnat started on the introductions and everything. Yeah.
Cool. Can everyone hear me?
Yeah.
Cool. I think it would be nice to go around the table, so as to say, with some virtual panelists as well as in-person ones. Just one line to introduce yourself or refresh the memory of the audience, and maybe one fun fact that you learned recently. Can be a fun fact about you as well. How about we start with Deepak?
Fun fact is the hard one.
So maybe instead of fun fact, we can say, if you had infinite budget, which robot would you buy to do your research or build?
Okay, so hi everyone. I'm Deepak Patel. I'm a professor at CMU, and I work on robot learning. If I had infinite budget, I would buy infinite robots, which are very, very low cost. I don't think budget should be a constraint for robotics. If we really want robots to be general purpose, we should go cost tending to zero, not to infinity. I like the answer.
I'm Chelsea. I'm assistant professor at Stanford. I'll do, well, one small fun fact is I learned how to drive on the left side of the road, including a camper van, which is rather large, like 3 days ago. And in terms of budget, yeah, I mean, I think that lots of robots would be great. I also think that I actually like robots that are lighter weight so that you can easily move them to different parts of the world. Also, robots that have a similar size to human hands and actually aren't too large. Actually, I really love that the Franca Amica Panda has been a really wonderful robot that we've used a lot, but it is also kind of somewhat large, and we've gotten a lot of use out of robots that have smaller fingers because they can do find things like open Ziploc bags or use zip ties or something like that.
I'm Dinesh Jayaraman. I'm an assistant professor at UPenn. Fun fact, well, I recently learned that New Zealand was only inhabited by humans about 700 years ago. That's, I don't know, it was a fun fact for me to learn. Robots. I really like the answer that Deepak gave about cheap robots. I think I would also have many cheap robots. But on a more, if I had to pick only one single robot, I think I'd pick a hand, because hands are at this point notoriously expensive, and there's not one that's very good. So a hand robot for dexterous manipulation.
With virtual, so we'll go with the order on our screen. So we'll start with Victoria.
Hi, everyone. I'm Victoria. I'm a PhD student at Carnegie Mellon. And if I had an infinite budget, I think I agree with what some of the other people said, like Deepak, that we should not be having infinite cost robots, even if we have infinite budget. I like the idea of having more robots and experimenting more with low-cost robots. Like maybe if I had infinite budget, I would try out a whole bunch of different approaches to soft robotics or something like that.
Laryl?
Hey everyone, I'm Laryl, assistant professor at NYU. Fun fact, I learned about how stop motion animation works recently, and it's really cool. So I highly recommend everyone to check that out. And in terms of infinite budget, I think I agree with having low-cost robots, but I think creating a good low-cost robot is going to be expensive. And so I would spend that infinite budget on creating that low-cost robot.
Okay.
Yeah, hi everyone. This is Haywan Park. I'm a research scientist and PI at MIT Media Lab, and also doing Amazon Scholar with Lab 126, the CoRL device team building home robots. I don't have the robot that I want to purchase at the moment, because if we do include imaginary robots, I do want a robot that can actually live with people, like support people, like socially, emotionally, physically, cognitively, all those aspects, but are also affordable so people can actually get them, right, eventually. So my imaginary robot, though I have like my other preferences, like for many reasons, Rosie is my dream robot.
Very nice, very nice.
I cannot hear Shikhar, but I think should I start with the first question?
Yeah, exactly.
Cool. Somehow your voice is a little lower on my side. Okay. I noted down a few open-ended questions which everyone can answer in their own light. They can cast this question however they want. But is there a simple tool, algorithm, trick that they think is severely underrated in our community right now that we should adopt more widely across robot learning? Looking at this as a hidden curricula or tips and tricks from the labs, which they use quite actively, but they think is not as widely known. It should be a simple thing, could be learning or not.
So one thing that we've been doing a lot recently that we very recently discovered is very helpful, and I briefly mentioned it, is using cameras mounted at the wrist of the robot. It seems to be magical and it really helps like the robot generalize. It helps efficiency in terms of learning as well. And the initial motivation for us for using it was that there's like so many things that humans can do just purely with tactile sensing. Of course, tactile sensors are kind of their own challenge, but one of the things that's nice about anything that's kind of centered around the hand of the robot is that and including tactile sensing, is that like things like this feel the same as like this. And so if you're trying to like grasp a water bottle, you will get kind of these really nice invariances, like 6D invariances when you train. And you get those sorts of invariances with wrist-mounted cameras and tactile sensors. And that's kind of my hypothesis for why it helps a lot. It also gives you a really close-up view. And so, yeah, a small trick that seems to help, at least in terms of manipulation.
I can mention, I mean, one trick I think is a very good trick, which I don't use often, but I would love to. I think this idea of residual actions, like not trying to output anything in the absolute sense, just output based on some other prior that you have, like this. If you have like some residual based controller, like residual RL or things like that, and I think that's a very cool idea. Second thing which we often use in our lab in across many projects is this structure of dynamic movement primitives. So because we worked on it, so we have paper on it, so we are able to very effectively use it, but I'm often surprised how much it is able to help. So for those who do not know, dynamic movement primitives is this like decades long work on trying to compress a dynamical, like a trajectory into a dynamical system, which is a parameterized, so you can just run it arbitrary frequency at test time, some matrix multiplication. Basically think of it as spline for robotics. So it's like spline and then we had some deep learning variant of that, which can just compress into a few lines of code. We use it quite often, and it's like one line in implementation details section, but it always seems to help with noisy data, which I think lots of people here are going towards, either from videos or from low-cost robots or from weak suboptimal demonstrations. From all these noisy sources, as data gets noisy, these spline-based techniques can effectively transfer with few examples.
Any virtual speakers? Daryl, hey.
Yeah. I think on the side of the robot, I think paying close attention to what your observation spaces and your action spaces is quite important. So Chelsea mentioned about the observation space, where if you have a camera on the wrist, it's really helpful. We have seen the same thing as well. I think even on the action space, right? Like what exactly is the output? Is it going to be like torques of the robot? Is it going to be end effector motions? I think on the robot side, that is really important. In the learning side, what we have found is sometimes the simplest of approaches actually works quite well. So example, if you just add, some clever augmentation on your data, it may help a lot more than a fancy learning algorithm. And similarly, if you just do simple nearest neighbors, it works in many cases a lot better than training a full parametric model on it. So yeah, so I think just having a look at sort of simple methods first before trying out your really complex neural network model, I think is a good trick to start off with.
Yeah, I have another action space related trick from the Toto benchmark train offline test online, which was presented earlier today. One of the simplest modifications to methods that led to the biggest increase in performance was outputting a trajectory of 50 actions at once instead of a single action, and then replanning it every time step. And across very different kinds of methods, that led to a huge improvement in performance.
Maybe one thing that I'll add is, I've recently been kind of surprised by the extent to which you can learn good visual representations on human-centric video data, like Ego 4D or something like that, that can actually translate to robots. I was for a long time skeptical that this would work out because we had image-based representations learned from like ImageNet or something like this for a long time, and for a long time nobody could really get it to work in embodied settings. But it turns out that there is some magic sauce to Ego 4D in particular, actually, that seems to get it to work. So this kind of ego-centric video data. And so we've recently we and others have been looking at this for maybe the last year or so, and there've been a set of surprising results that have shown that you can actually get really good performance out of these representations. So it can reduce policy learning to be basically behavior cloning from just a small number of demonstrations afterwards.
I think this is a great segue actually into one of our themes, which is talking about pre-training. So the role that pre-training plays when we want to deploy robots in the real world. So this team, Annie will ask the questions on pre-training, and then we'll start the opening question, and the audience can jump in as well.
Yeah, Annie, take this away.
Yeah, so I guess it's obvious that pre-training plays an important role, especially in allowing for efficient adaptation at test time. One could say that currently a lot of the dominant pre-training schemes are task agnostic and based on kind of self-supervised objectives. Do you have thoughts on how we can design better pre-training schemes that might kind of account for test time in mind? Yeah, and whether we should do this.
I can talk about what a line of work that that we are currently building, and there are others at the table that also have similar work. Yeah, I think the right way to train representations after having done this work, I'm coming around to thinking that the right way to train representations is to train them basically as value functions. Like the representations are basically intended to tell you how far away you are from a goal. So you can think of this as some kind of goal conditioned value function where you're providing, let's say, an image of where you want to be. And where you want to be in the case of human video is simply the last frame. So the humans are showing you how to get to that last frame in the video. And your value function now is simply the distance in representation space. And that's how you train your representations. So we find that this method of just using TD learning to learn a value function, train a representation as a value function, as an implicit value function, worked really well for us.
I guess one thing that I could add is I think that, I mean, Annie was specifically asking about task agnostic, and I do think that like some of the most successful pre-training schemes in vision and NLP have been fairly task agnostic, in that they don't like specifically, they're not specifically for like sentiment classification or something like that. And so I think that the things that are self-supervised and get the most power out of unlabeled data are going to be the most promising. That said, ideally, I think it would be tailored towards robotics, tailored towards control, and like learning value functions, I think is one example of that. I do also think that there could be some kind of interesting approaches for priming representations as well. And so with like prompting, for example, we see that you can kind of prime models to act in certain ways, and maybe we could have the same thing for robotics where we have a form of pre-training with a form of prompting or priming that kind of tells it, this is the task I want you to do, and maybe that it can focus its representation on the parts of the scene that are most relevant and ignore all the distractors. And maybe we could get the generalization benefits, extra generalization benefits and robustness benefits if we have those sorts of representations.
So I would just add something to this point. So I totally agree with Chelsea and Dinesh's point, and both of you have done amazing work in like getting this representation. I think what we are missing less work as a community is that when we look at data out there, whether visual, like videos or images, we always go for representation of vision, much in language and things. But there is another strong signal that we have in videos, which we usually ignore, and value function does try to capture it, is this prior for actions. Like somehow if you look at your nephews or nieces or your kids, they go around the house and do all the wrong things. They will put their finger in the sockets, because they know something interesting is there, like because they've seen people do it. They will open the door at the right place. They know to touch the knob and not to the other hinge. So all this knowledge is there in videos where you can extract a very strong prior for actions as well. And it's not just representation. All the representation is also very important. And I think that I'm really excited about, and we are doing a lot of work in that direction. This whole concept of affordances goes back to 70s and 80s, and this work from James Gibson, J.J. Gibson, in arguing about affordances of the world. We can extract a lot of this information by just watching people do stuff, because that tells us what environment is capable of offering to humans and pretty much to our robots as well. So this abstracting action representation from videos is another topic in addition to the visual representation and value function, which I think is very valuable.
Thanks first from the virtual panelists. Hey, Laryl, Victoria.
Yeah, so maybe just to take a contrarian view over here. So from a lot of our experience, we have found that, just pre-training our models on like ImageNet pre-trained models or some off-the-shelf like a VIT model which has already been pre-trained actually gives us a lot of initial boost. And then to sort of overcome in-domain examples, doing some additional amount of self-supervision on in-domain data helps a lot. So in a way, I'm not sure how much is retraining on something like Ego 40 helping over just like having a little bit of more data on your task domain and just doing some small amount of self-supervision on that task domain. So I guess if I had to train a model for like overnight, instead of training a model overnight, I might as well just have few more demonstrations in that domain and try to make my model more attuned on that domain. So I think that's an important question about what's the value of time, right? Like if I say that, okay, I want to train a task in 1 hour, do I want to fine tune some other model, or do I just want to get some additional data on my new task?
From a meta level, I think benchmarking is also really important when we think about vision representations. And so one thing the Toto benchmark provides is a way for people that maybe don't want to develop their own actual policies or set up their own hardware to contribute vision representations for the vision part of our benchmark. And so you can actually do that. If you're interested, you can go and download our data and try out different vision representations on it. And I think we've done a number of generic representations. We also had a contribution from Laryl, and that was one of the best performing right now. So if you want to counter Laryl's point, you can try your own.
I'll say something else about representations. Even though I mentioned that we are quite happy with the representations we currently have, I always have this sneaking feeling that we are going about representations the wrong way. In that we're always building these kind of unstructured vector representations when we are using neural nets. And I think some of the older ideas about representing the world in terms of objects and in terms of entities in the scene, objects, their subparts, and so on, are actually on the right track, and that we need to somehow bring together a fusion of this kind of end-to-end learned representation and policy together with these kinds of object-based abstractions of scenes. So this is something that I've been trying to get my students excited about, and some of them are. But hopefully some more in the room as well. So what we want to do is basically build hierarchical entity-based representations where you can, let's say if I have a robot that's trying to fold a pile of laundry, at some point the robot can just see the world as a pile of laundry, and at some other point it can start to see the world in terms of individual clothes in that pile, and then at some other point it might start to see the individual folds in the pile of cloth. And it has to be able to make those decisions. It has to be able to access those different levels of abstraction of the scene at different times, depending on the task that it's trying to solve. And I think that kind of reasoning it makes the most sense when you try to attach to real particles in the world. Like your representation needs to somehow be bound to real objects and entities in the world. That's kind of a something that we're pushing for.
We'll open up questions from the audience. If anybody has any questions, feel free to raise your hand. Yeah.
So what do you think well, the large language model and language model
Yeah, that's an interesting question. So yeah, certainly semantic.
Hey, could you repeat the question in the mic, please, for the virtual audience?
You want to maybe some of the question?
Yeah. So if I understand the question correctly, you're basically asking how do language models interplay in these entity-based representations?
Yeah. So that's my understanding of the question as well. So I certainly think that language models have something to say about the semantic level of entity-based representations, right? So the semantic level meaning the stuff that has language for it, right? So object names, for example, are only assigned to not necessarily to like this portion of the monitor, but the whole monitor as a whole, right? So for some level of this entity-based representation, I think that language models will certainly help. And we are already seeing this, for example, in zero-shot visual object detectors. It's possible now to use the implicit knowledge in large language models to train zero-shot object detectors that will just say, given a particular word as input or a phrase as input, it will detect that object in the scene. But this can't really work for specifics like that little fold on a piece of cloth in that file that I was speaking about, right? So at some point, yes, the semantic level of this entity-based representation can likely draw from large language models, is kind of what I would guess.
Doesn't the kind of success of language models suggest that maybe we shouldn't kind of explicitly build an entity-based structure? Because I feel like these models, they don't, I mean, in the old days of NLP, I'm not an NLP expert, but people would build these kind of entity-based structures like trees and so forth, of syntax and so forth. And it seems like they kind of already implicitly represent that through large-scale self-supervised pre-training. Has that changed your view at all, or?
Well, I would say in the context of at least representations for robotics, right? I find it to be extremely useful to have somewhere where you can probe in the pipeline and know what is going on, rather than relying purely on the eventual action coming up. Especially in the context of real-world RL, where we're concerned with issues like safety and operating around humans and so on, it seems more and more important to have some level of interpretability, both in terms of why did my robot do this thing, but also interpretability in the sense of how should I build an algorithm such that in this part of the pipeline, it does this thing, and this other part of the pipeline, it does this thing, which are both important for my task. Like representing the objects is certainly important, representing interactions between objects is certainly important to, let's say, solve some prediction task in my dynamics model. But how do I actually even build in those biases, right? And it seems important to make some distinctions there.
I would use this to mention one of the other secret tricks I really like. I think this is from Sergey and Kelsey's deep visuomotor paper, the special softmax trick. I think it's kind of underappreciated, but that is one of my favorite part of that architecture, which I think you guys use across many papers afterward. Like that's one way to get entity based thing, which is not that not that of a strong segmentation or anything like it can emerge to give focus on the. So this is one way to get entity centric probably, which is not too restrictive, and I really like that.
I absolutely agree.
I think I'm mostly trying to move away from it at this point, but the I do think that kind of interpretability is kind of generally underrated. It's like super useful to be able to understand what the network is doing, what it's perceiving and so forth. And so that was one huge benefit of that architecture. And we actually had a live visualizer sometimes that would actually show us where are these kind of key points looking at, and that would tell us like, has it learned a good representation? And also a lot of the work that we did on visual model-based RL, where we could actually visualize the predictions from the model in image space, was like super valuable for like understanding if the model was underfitting or overfitting or what. And I think that actually with model-free RL, we don't have interpretability, like nearly as many interpretability tools for understanding how good the algorithm and how it's operating. And I think that if we had more of those tools, it may allow us to make more progress.
Any more audience questions? We'll probably take one more and then move on to the next topic. Yeah. Oh, yes. Whoever wants to go.
I guess I was just wondering, you talked about representations a lot, but you haven't really mentioned like anything related to causality and like being able to learn. Like, is it representations we want, or is it causal models that are fitting into these representations? Like, how do you know it's a good representation besides just better reward at the end of some task?
I would say these two are not in contradiction to each other. Like good representation is part of a good causal model or word model, however you want to call it. I think one cannot exist without the other. Like for instance, usually when you find that your model works really well, you will find the representation it has learned are also very good. And vice versa will be true if you had like, some data on training the model. But yeah, I personally don't see them in contradiction. I think both, like if it was possible and we had data for robots, we could just learn representation by training good world models. but maybe the data we have is not ideal to just build world models directly. Action is missing, many other things in videos, for instance. So like value function, etc., are one way to bootstrap the world model. If we had a good world model of the whole world, there's nothing to do in robotics at that point. We can just, so basically search problem. We are back to search inside that world model.
I haven't thought a lot about that question, but maybe I can add a note. So my guess is that the most parsimonious, the representation that leads to the most parsimonious, fuzzily consistent dynamics model will be something that abstracts the world in much the same way as we do, in terms of like objects and entities and so on, and their interactions. Because I think that's kind of a fundamental reason why we experience the world in that way.
So yeah, so I think this is a good segue, into from looking at the causality of the physical world to actually discuss more about the physical world. So Annie, you want to ask the next question?
Yeah, so I guess this next question kind of ties back to one of the themes of our workshop. So a thesis of our workshop is that there will always be a mismatch between training time and test time when test time is in the physical world. So it seems natural to kind of somehow incorporate the real world into the learning loop. If you kind of agree with this, where do you think the physical world should be embedded in this learning loop? Should we just solely learn in the real world, or should we only deploy once? Yes, what are your perspectives on this?
Maybe we can have one of the virtual speakers. I think something went wrong with Hayes' internet, so well, maybe we can start with Laurel or Victoria.
Sure. Yeah. So I think it really it depends on what exactly the context is over here. For example, if you're training, I don't know, a surgery robot, you don't want to learn in the real world. But for sort of problems where it's not safety critical, I think learning in the real world has already shown to work, right? So you can sort of imagine something where using all the priors, all the imitation data, all simulation, everything you can start off with an initial policy, run it in the real world, see how well it matches what you think it should do, and then use that signal to fine-tune your policy until it does well, right? So at a high level, a strategy of that sort seems like a reasonable option. But again, of course, it depends upon what exactly your problem domain is and how much time you have to interact in your environment.
Yeah, I agree. I think some combination of offline learning and fine-tuning that policy afterwards is a good idea. And in addition to whether the system is safety critical, it might also depend on kind of the scale or the cost of that system. For example, I don't think we're going to have the ability to do that much online adaptation in like a fusion system.
Fortunately, a lot of manipulation systems, or sorry, a lot of robotic systems are not in safety critical settings, and in those settings, I think that it makes sense to learn a lot in the real world, with some basic safety precautions in place. I think that a lot of times we talk about kind of data efficiency in robot learning, and we talk about data efficiency as like a really good thing, and I think that the amount of online data that we need, the amount of data that we need to collect from a particular policy, that we should make very small. We should ideally be as efficient as possible with the online data that we need to be collecting. But on the flip side, I think that in terms of offline data, I think that we should be using as much offline real data as we can, because that's data that we could reuse repeatedly, and it's not costly to use if it's already been collected, if it already exists. So of course, if it's offline data from your exact environment, that's not practical. But offline data from other robots, other environments, other tasks, and so forth, in general should be very cheap if we kind of start to accumulate that data and reuse that data. So in terms of learning in the physical world, I think that ideally, like, we'll have lots of physical world data in some offline form. And then I think that there also should be some learning that happens online at test time, but ideally something that's very efficient so that it doesn't take a lot of time.
Yeah, I'll add one thing to that is, like, when you're learning in simulation, right? One challenge of learning in simulation is not even getting the physics right, because in many of these settings we actually do have reasonable physics models, maybe not of the details of like contact at the edge of, at the edges of the phase transitions, but otherwise we do have reasonable physics models most of the time. But one challenge tends to be actually just having the diversity of data that you would experience in the real world, right? So if you want your kitchen butler robot to work in every kitchen in the world, that's actually a really, really hard thing to set up in simulation and train on diverse data for. Right? So at some point, you're going to have to do learning in the real world just to get it to work for kind of general real world settings.
One of the things that I'll add here is that I think that there are a number of scenarios where you can simulate the physics. And I think that for those of us that are doing robot learning in the real world, I think that we should actually prioritize scenarios that are very difficult to simulate the physics, because those are the scenarios where learning the real world is imperative and where we can't do it any other way. Things like skewering broccoli with a fork, or feeding a person, or kind of opening a Ziploc bag. These sorts of things are really challenging to simulate, at least faster than real time. And if we can show that robots can learn how to do those things in the real world, it'll really make the case in a strong way to the robot learning community, and hopefully get more people in this room.
I think every room is like this. I think I agree with all the points, and I think everything's covered here.
So we were originally supposed to end at 45, but we can take a couple of audience questions, and we do have a poster session after this. But first, we can maybe start with 1 or 2 audience questions as well. Thank you, Deepak. Yes.
Do you think it will be like general everything, or the rest of it really has to be connected? Let me give an example. For example, it's also about evaluation. But if you want to do like take and place, presentation will be very different from, let's say, if you want to do like cleaning up the table. So if you want to clean up the table, you may want to represent the dots on the table, but then that is in vain if you just want to place of objects. So like, since we are talking about representation, do you think that the task-dependent representation learning is useful, or definitely that's useful? But do you think there's is that a direction to go, or do we want more like general representation?
So yeah, that's an interesting question, and I've recently.
Could you repeat the question or summarize it for the audience?
Well, let me restate the question, and maybe you can help me if I'm missing some part of it. So as I understand it, the question is, okay, there's a trade-off between the generality of a representation as you might build for let's say an auto-encoding loss from an image, right? So you might say you're capturing all the information there, versus there is task-dependent representations where you might say, I actually want to only focus on the table if I'm cleaning the table, and if I have a bunch of objects on it, they don't particularly matter at that time, for example. And so, should we be learning, instead of these general big representations that capture all of the information in the scene, should we instead be learning some kind of task-specific representations, right? So yeah, I think that's a really interesting question. And yeah, the way that I've been thinking about it recently is we do still want to have general representations. We want to have representations that capture all the information in the scene, but it should be organized in some useful way. So this kind of object-centric hierarchy that I was talking about is kind of one way of organizing the information in a useful way, such that I could choose for one specific task, either through manual intervention or by learning, I could choose to pay attention, let's say, only to the pile of cloth representation of the laundry on the table, But at another time, I might choose to instead pay attention to the much lower level of representation that instead says, I want to pay attention only to the specific folds in one particular piece of cloth and not care about anything else in the scene. So it has to be, I think the information has to, the representation still has to retain all the information in the original raw input because it's going to be useful for some task or the other. So it's still a general purpose representation, but it should be customizable by organizing the information in a useful way. So how do you exactly disentangle different pieces of that information in such a way that you can kind of assemble dynamically the task-specific representation from this more general representation afterwards? That I think is kind of the kind of nice, interesting way to think about it. Yeah.
Kind of related, I think, to when one in general, how important is school? Like, people think is to be able to learn policy, or the model offline, or we go online to be able to ensure some kind of safety. So you look at people that work like quality control rather than systematic control. They're all about system ID, and then we're going to work out some absolute tolerance of it. Whereas we can just about like violating constraint. You can do it policy, it's harder to do. Which is we can do the policy, we can't do it like a model. So we're going to what do you guys think? Like, is it important to learn a model offline to then go online, send quick tasks? And is it like work that's running these models?
Yeah, so the question was, is it important to learn a model specifically offline when you move online and specifically in safety critical tasks? So I guess my perspective on this is that well, I mean, it really, I think that the answer may depend on the application and what safety critical tasks you have in mind. From my experiences, there are a couple things that could be useful. So one, you could try to learn a model. I love models a lot in some ways because they're quite flexible. They allow you to plan to solve lots of different tasks. They allow you to plan to avoid certain states without having to kind of have explicitly pre-trained a policy for that. And I think that's amazing about models. I also hate models in that if you have like raw sensor observations, like learning models in image space is really, it's challenging. And you need large models, they're expensive and so forth. So I think that there are pros and cons. One other thing that I'll mention, since you brought up safety specifically, is we've done some work on learning Q functions of that estimate the probability of kind of a constraint violation. And that's something that you could learn offline. Most of our work has learned online, but there's some work by some folks at Toronto and Berkeley that learned these sorts of safety critics offline as well in a conservative manner. And that is, I think, a much lighter weight way to try to transfer knowledge of safety into an online learning context. Yeah, it gets away from having to learn like a full model of the system.
So I agree with everything that Chelsea said, and maybe I'll add one other thing that's kind of maybe also partly plugging something that we did a year ago. We have these, we found that it's actually quite easy to train models rather than only predicting the next state to also predict whether or not that state is something you like. So in the context of like something like CoRL, where you might have a set of safety critical safety constraints that basically say there are some states I like and some states I don't. It's quite easy to train this model to additionally output this secondary label, aside from just predicting the next state of whether that next state is going to be nice or not. And you can use that in your planning algorithms afterwards, and it seems to help quite a lot.
So I think some of our panelists do have to go. So and we are about to start the poster session. So let's just thank all the panelists for coming. Thank you so much. It was a great hearing your thoughts on all these topics. Yeah. Yeah, we're about to start the we're about to start the poster session. We just need to get all the get all the TVs from the workshop the workshop chair. So we'll just get that, and maybe by 4 I think we'll be ready for you guys to set up and we'll have a poster session for 1 hour 15 minutes. Thank you everyone again.
Thanks for organizing.
Yeah.